Hello everyone, my name is Sebastien Arbogast. I'm a blockchain trainer on Udemy and a public speaker at ChainSkills. And today I'm going to show you how to develop your first smart contract and decentralized application on the Ethereum platform. Together we are going to build this application from scratch, and I'm going to show you how it can be different from developing a traditional web application. Now, the project we are going to develop together is called Crypto Series. And you can think of it like Patreon, but without Patreon. Now, if you don't know what Patreon is, it is a crowdfunding system for recurring creations like YouTube series, podcasts, and so on. So creators can publish episodes of a show, and then their community members can decide to support the show financially, so that each time a new episode is published, the creator receives a small amount from each supporter. Now, with Crypto Series, supporters will be able to pledge Ether to a show, and creators will get paid in Ether as well. And since it's decentralized, there is no commission to pay to a middleman, so the totality of pledges will go straight to the creator. And a certain number of rules will also be implemented in the smart contract that corresponds to an individual show with many episodes. And you will see that authentication of the members, controlling who can do what at which point in time, payment from supporters to the show creator will all be handled automatically by the smart contract, without any third party involved. How cool is that? Now, by the way, everything I will show you here is self-sufficient. It will give you a nice introduction to a real decentralized application on Ethereum. So real, in fact, that we are going to use it soon in production to fund the French-speaking podcast we produce with ChainSkills called Proof of Cast. And a complete version of the source code of this project will be available on our GitHub repository at the address that's in the description down below. Now, of course, if you have any question or suggestion for additional content, don't forget to like this video, comment, and subscribe to this channel to be notified of future videos. That being said, if you want to go further, really understand the blockchain environment, how to create more advanced projects, deploy applications to other test networks, and even production networks, learn how to unit test your smart contracts and so on, we also have a 15-hour video course on Udemy with more than 11,000 students and 2,100 reviews. And you can find a link to this course with a nice discount in the description down below. Now, are you excited to start? We sure are. But before we start, let's have a look at the agenda for this tutorial. First, we'll quickly have a look at the architecture of our application to see how all the elements fit together. After that, we are going to install a couple of tools that will make up our development environment. And then we are going to create a new project and look at its structure. With that in place, the next step will be to create our smart contract, to store the data for an individual series, and handle payments, as well as notify users when something changes in our contract state. Then we'll deploy our smart contract to a development Ethereum node. And finally, we are going to develop a very simple web user interface to interact with our smart contracts using only jQuery. So with that laid out, let's jump right in. So first of all, let's talk about the architecture for Crypto Series. A decentralized application is usually made up of two components. A user interface that can run in the browser or in a desktop application, for example, and a smart contract that acts as some sort of a backend. But this smart contract has a few key differences compared to a traditional backend application. First, it doesn't run in a single application server, but on all the nodes of a distributed network. In development mode, we will usually emulate the whole network with a single node running locally, with some added introspection capabilities. And I'll show you what Ganache is later. The second key difference is that once you have deployed the smart contract to this network, there is no turning back or changing the way it works. You can change the data that the contract contains, but not the way it works. So if there are bugs or if you want to add features after the fact, the only thing you can do is deploy another version of your contract in a new location and deactivate the old one. And again, we'll show you how to do that in this tutorial. And the last key difference, the third key difference, is that inside the Ethereum node we will send our smart contract to, there is a special virtual machine called the EVM, or Ethereum Virtual Machine. And in that virtual machine, every single operation that modifies data has a cost, and this cost is measured in gas. The goal of that mechanism is so that you cannot bring the whole network down with something like infinite loops, for example. And you have to remember that your smart contract code will be executed and run on every single node in the network. So, to sum it up, let's look at an architecture diagram. So we'll have a web application written in JavaScript, HTML, and CSS. The JavaScript itself will interact with our local Ethereum node through an HTTP API, encapsulated in a JavaScript library called web3.js. And in our development setup, we will just use one emulator node, but in a real setting, synchronization of smart contracts and their state would be handled automatically and transparently, so it's not really a concern. So to do all of that, we need three main tools. We need a browser extension to be able to handle all the cryptographic keys, and our wallets, basically, and also the connection with our Ethereum node, and that will be MetaMask. The second tool we need is an Ethereum node emulator that serves as an Ethereum development environment, and this will be called Ganache. And we also need a build framework to help us compile our smart contracts and deploy them to our Ethereum node. And this will be called Truffle. Now, in the next step, we'll install Ganache and Truffle. And for MetaMask, we'll wait until we actually need it to start working on our front-end application. So now let's start installing our tools, and the first one is Ganache. Now Ganache will be our Ethereum node emulator. It has a very explicit user interface, and it is designed to make testing our smart contracts easier, as it adds a certain number of tools that let us inspect what is going on with our node. So in order to install Ganache, you need either Linux, macOS, or at least Windows 7. And you can find all the instruction on this website, so truffleframework.com/Ganache. In our case, we'll install the macOS version. So I already downloaded it before. It's on my desktop. That's it. So I just drag and drop it to the applications folder. And now I can go to applications, find Ganache. I'm going to add it to my bar here, and I can launch it. Okay, so in that case, that's version 1.2.1. You might be using a more recent version, hoping that they did not change too much of the behavior in the time being. I mean, in the time between the time I'm recording this video and you're watching it. And that's it. So when you start Ganache, it runs an Ethereum node in memory, meaning its state will be completely refreshed every time you restart Ganache. Also, by default, it has auto mining on, which means that it will wait for transactions to be sent to it before it creates new blocks. It's good for development because it makes transactions almost instantaneous. But in our case, since we want to wait a certain number of blocks between two episodes, our node should be closer to the real deal. Meaning that it should mine blocks at regular intervals of time, whether they are pending transactions or not. That's how the main Ethereum network works. Thankfully, we can change that very easily by going to the settings in Ganache, disabling the auto mine feature, and then setting a mining block time. And in our case, we use a 1 second mining block time. Then I hit save and restart. And now we can see that the mining status is 1 second block time. So that means that from now on, this node will mine one new block every second, whether there are transactions in a block or not. And that's actually how the main Ethereum network works, except that blocks are 15 seconds apart on the main network. The second tool we need to install is Truffle. So Truffle will be our build framework, kind of like Gradle or Maven, but for decentralized applications and smart contracts. We'll use it to create our project and initialize it, to compile our smart contracts, to deploy them to Ganache, and also to interact with the deployed contract. Note that it can also be used for unit testing contracts, but we won't have time to show that in this video. So to install Truffle, you first need to have Node.js installed on your machine. There are very different procedures to install this depending on your environment, so I won't go into details on that. I just invite you to have a look at nodejs.org and at the right procedure for your system. I installed the current version, and I'd advise you to do the same, not use the LTS version, which is a little older. So once you have installed Node.js on your machine, if you go to the terminal onto PowerShell on Windows, I strongly advise you to use PowerShell if you're on Windows. But in the Bash terminal on macOS, I can run node -v, and indeed I have 10.6.0, or npm -v to check the version of the Node package manager, which we'll use to install Truffle in a second. So again, note that there is no advanced IDE for decentralized application development yet. So our best option is to use just a basic text editor and a command line for most things. Most text editors have a plugin for syntax coloring for the Solidity programming language, which is the programming language we'll use to write our smart contracts. In our case, we are going to use Atom as a text editor, but there are such plugins for IntelliJ, for Visual Studio Code, and a whole slew of others. So if you already have your text editor that you're familiar with, feel free to use that one and search for a Solidity plugin for it. So to install the latest version of Truffle, we can use the terminal and run npm install -g to install it globally on our machine, and Truffle is the name of the package. So at the time of this recording, we are actually installing Truffle 4.1.13. If you want to be sure that all the outputs will be identical, in case new versions of Truffle have come out since then, you can easily install a specific version of Truffle with npm install -g, then the name of the package at 4.1.13, for example, to install this specific version. And then once it's installed, you can run Truffle version to check both the version of Truffle itself, which is 4.1.13 in our case, and the version of the Solidity compiler, which is 0.4.24 for this tutorial video. So now that all our tools are set up, let's create our project. I'm just going to clean things up a little bit. So the first step to creating our project is to create an empty crypto series directory. And we can do that directly with the operating system commands. So for example, in this terminal, I can run, so I'm on home right now. I can go to my desktop, for example, and then run mkdir crypto series. That's the name of the project. So note that Truffle won't create that directory for us. We need to create it and then change directory into crypto series. So now I would use a special feature of Truffle that is called boxes. And you can see boxes like project templates that will make it easier for us to integrate our smart contracts with other tools. In this case, we'll simply use the Webpack box. So we can run Truffle unbox Webpack. Again, from within the crypto series directory. So this command downloads the project template from GitHub and sets up all the files in our directory. Note that these boxes are maintained independently from the version of Truffle that you have installed on your system. So if you are working with an older version of Truffle, it might be out of sync with the project template that unbox downloads. If that's the case, just make sure your files are exactly as we will describe in this tutorial. And as you can see, once the project initialization is successful, there are a certain number of commands available to us. Now let's open this newly created project in a text editor to see how it's organized. So I'll use Atom to do that and just open the current directory. So if we look on the left side of the screen, we can see the project structure. So in the root directory, we have the app directory. That's where we'll put all our front-end files. We'll also have the contracts directory, and this is where our smart contracts will go. We also have the migrations directory, and this will contain all our developments, our deployment scripts. And in Truffle lingo, deployments are called migrations. We also have the node modules directory, where all the dependencies, especially the npm dependencies, are downloaded. We have the test directory that contains all our unit tests. Then we have a couple of configuration files for ESLint. We have a couple of images that we won't need. So by the way, if you want, you can delete those. Then we have package lock and package. Those are npm dependency declaration files. We have truffle.js. This is the configuration file for Truffle itself. Especially it allows us to configure all the networks that we are going to use for development and then for deployment. And finally, we have the webpack config file that configures how our front end will be built and packaged. Also note that this template project already contains a couple of smart contracts, so you can see those .sol file. The .sol is the default extension for Solidity files, and we can already see a couple of contracts here. So migrations.sol is a special smart contract that is needed by Truffle to keep track of what's already been deployed to minimize the risk of overwriting stuff. You should keep this contract there and you don't touch it for now. We're just going to show you a small modification that we need to make later on. Now, Metacoin and ConvertLib are just sample contracts and we won't need them, so we can actually delete those two. So we are only left with our migrations.sol contract. And in the migrations directory, we also have two deployment scripts already. We have one initial migration.js, and this one is used to deploy the migrations contract, which Truffle will need. So we should never touch that script, and it should always run first. And that's why it has a 1_ prefix, since all the scripts in that directory will be run in alphabetical order. And we also have a second deployment script that's called deploy contracts, and this one deploys the ConvertLib and the Metacoin contract. So since we just deleted those contracts, we can also delete the second deployment script. And finally, in the test directory, you can delete both metacoin.js and test-metacoin.sol, because again, they are there for testing the Metacoin contract that we just deleted, so we can delete those two files. Now the next step is just to customize truffle.js. Okay, so by default, the Webpack box configures a development network that is accessible on port 7545. Now, this development network corresponds to an Ethereum node run by Truffle itself, but it's not Ganache, meaning it doesn't have a nice UI that makes our transactions easy to inspect. So let's rename the development network into Ganache. So here we just change the key in that JSON object. And we can keep the rest of the parameters the same, since Ganache also runs on port 7545. We don't forget to save that file. And now Ganache is launched, it's running. So our development environment and project are now ready to start implementing our first smart contract called Crypto Series. So to put it simply, a smart contract works just like a stateful singleton service. It has state variables that can only be modified by functions that you defined inside your smart contract. It also has a constructor that is executed when the smart contract is deployed to the blockchain. And it has functions that can read or modify the state of the contracts, but also call functions on other contracts, access details of the transactions that triggered them, and transfer cryptocurrency around, among other things. So in our project, we'll have just one contract that we will call Series. And we can create that contract with a command. So let's go back to the terminal, clean things up a little bit. Oops. And run the command Truffle, create contract, and we call it Series. Now, if we go back to our text editor, we can see that a new contract was created in the contracts directory. So just a small description of what we already have here. So the pragma here is used to specify the minimum version of the Solidity compiler that needs to be used to compile this contract. Then the contract keyword is basically like the class keyword in other languages, and it declares our series contract. We have a constructor that does absolutely nothing for now. And all of this is in the Series.sol file under the contracts directory. And of course, as we said before, .sol is the default extension for Solidity source files. Now let's add some functionality to our contract. And the first thing we are going to add is immutable state variables. Okay, so the first thing that this contract will do is store its own state in the form of state variables. And we'll need to store 3 variables to configure the working parameters of the contract. We'll have a title that will store the title of the series this contract instance will fund. Then we'll declare an unsigned integer state variable called pledge per episode that will store the amount of cryptocurrency that the creator of the series will receive from each contributor for each episode. And this amount will be expressed in the smallest possible subdivision of Ether that is called Wei, W-E-I. And 1 Wei corresponds to 10 to the minus 18 Ether. And finally, contributors will also be able to pledge support for several episodes at a time. And we said we wanted to protect them from creators who might pretend to publish a lot of episodes in a rapid succession to run away with all of their supporters' money. And to do that, we need to store a value corresponding to the time that the creator will have to wait after publishing one episode before he can publish the next one. But since the blockchain is distributed across the network on a lot of computers, there is no guarantee that the clocks of all those computers are in sync. The only sure thing is that the number of blocks in their blockchains will be in sync. And since those blocks are designed to be produced at regular intervals of time, about 15 seconds on the Ethereum main network, we'll express this period, so the duration between 2 publications, between 2 episodes, in number of blocks. And of course, on our development environment, time will be faster because we configured our block time to be 1 second. But that's okay. It's actually a big advantage because then we won't have to wait that long. And we'll call that variable minimum publication period. So let's declare those 3 variables at the beginning of our contract. So again, the first one is a string. It will be public and called title. We'll also have a uint, so that's an unsigned integer public, and it will be pledge per episode. And finally, uint public minimum publication period. By the way, we made those 3 variables, state variables public, which means that the compiler will automatically generate read-only getters for those variables for us, but no setter, just getters. And those 3 state variables will be initialized at deployment time, but once our contract instance is live, nobody should be able to change them. So let's define their values through constructor arguments. So in the constructor, we can add a couple of arguments and just call them slightly different. So string underscore title, uint underscore underscore pledge per episode, and uint underscore minimum publication period. And then in the constructor, very simply, we'll just assign those values. And finally, minimum publication period equals underscore. So this is very close to other programming languages that you might be used to, like JavaScript and so on. And also, we'll make this constructor public, so that it can be called from outside and not just from within the contract. And again, we just declare 3 arguments, and the value of which is copied into our state variables. And we'll see later how we'll call this constructor. Okay? So the next thing we need to do is define the interface of our contract. In other words, which operations our contracts will expose to the outside world. And there are basically 4 of these operations. First, a supporter must be able to send some money to the contract in order to pledge for a certain number of episodes in advance. And the minimum will be 1. This will be the pledge function, and this function will be marked as payable to indicate that callers need to send some money when calling this function. So let's declare this function now with the keyword function. It will be called pledge. It's public, so it can be called from outside the contract, and it's declared as payable because, again, people who want to use that function, call it, will have to associate some money with this call. And we'll show you how to do that in a minute. Okay, the second function will allow a supporter to withdraw the money he pledged, that was not sent to the creator yet. And this withdraw operation, of course, will allow him to withdraw his own money and not anyone else's. So let's, for now, just declare that function withdraw. And again, it's public, and this one is not payable. Now, the third function will be reserved to the creator of the show, who should be able to publish a new episode, and when he does, he should be paid pledge per episode times the number of supporters who still have at least pledge per episode in their pledge. And we'll show you how we maintain that later on. And that will be the publish operation, and it will take just one argument that will be the link of the episode, and this will be a string. So function publish, and it takes string episode link as an argument, and the function itself is public. And finally, in case the creator decides to terminate his show, he will be able to close the contract. And this will send their pledges back to all the contributors and also deactivate the contract. And this function will be called close. No argument, but it needs to be public. Now, of course, the publish and the close operations should only be accessible to the creator of the show, who is supposed to be the person who deploys the contract, and we need to keep track of that. Now, of course, the publish and the close operations should only be accessible to the creator of the show, who is supposed to be the person who deploys the contract. So we need a way to keep track of who deploys the contract, that is, who calls the constructor, and then check that only he can call certain functions, like publish and close in our case. So let's try a first implementation of that. In Solidity, an account, whether it's a contract or a normal account, is represented by an address-typed variable. So let's define a state variable called owner with an address type. And again, this address can be either the address of a contract or the address of a human-controlled account, if you want. Then to know who called a specific function or constructor, we can use the special variable msg.sender that's also of type address, and we can call that variable from within a function or constructor. So let's add the following to our own constructor. As a first instruction, we can initialize owner with msg.sender. Now that our contract owner is registered and nobody can change it after the contract was deployed, we can check who calls each of the creator-specific function and throw an exception if it's not the owner. So for example, at the beginning of publish, I can add require msg.sender equal owner. And I can do the same thing at the beginning of the close function. And again, what that means is that we will check that the sender of the message, meaning the person who calls this function, is the owner of the contract, so the same person as the one who deployed the contract. And if it's not, require will throw an exception and interrupt the execution of that function. So anything that comes after will not be executed. Same thing in the close function. But actually, there's a better way to check who's calling those functions and throw an exception if it's not the right person. A reusable way. And this way is called modifiers. So we can declare an only owner modifier at the beginning of our contract. So for example, here, modifier only owner. So it works almost like a function. Here we can have our require msg.sender equal owner. And then we use a special instruction in the form of an underscore. And this underscore actually represents, it stands for the code of the function on which the modifier will be applied. And to apply that modifier to our functions, we can just modify them like so. After the public keyword, we add only owner. That's the modifier we just defined above. And we do the same thing with the close operation. And with that, we can simply remove this from the function. And it will be exactly the same thing. So as you can see, by using a modifier, we're able to make our access control logic reusable and to completely externalize it from our functions so that they focus on their business, knowing that only authorized users can call them. In fact, this access control logic is so popular and generic that there exists a reference implementation, and we can reuse that reference implementation. And that implementation is called ownable. Now, the ownable logic is implemented as a smart contract from which our own contract will be able to inherit, because yes, Solidity supports inheritance and even multiple inheritance. So the first step to reusing the reference implementation of ownable is to install the dependency using npm. So we can go back to the terminal and type npm install -e, and we'll install a dependency called OpenZeppelin -solidity. So OpenZeppelin is a very renowned smart contract developer and auditor that created a framework of smart contracts for all sorts of generic use cases, from simple practical things like ownable to more advanced things like ERC20 tokens. Now the command above will download those reference contracts locally into known modules. After what we can import ownable into our own contract. So right after the pragma, if we go back to the contract, right after the pragma, we can use now import, and we'll import it from OpenZeppelin -solidity /contracts /ownership /ownable.sol. Okay, so here we are just importing the Solidity contract that's defined in this file. And Truffle will know where to look for this dependency because everything is configured for us. And the last step is just to declare that our series contract extends ownable, which we can do with the is keyword. So here in the contract declaration, we can simply add is ownable. And that's it. Now, if you want to check what this contract does, we can go to Node Modules, go down to OpenZeppelin Solidity, Contracts, Ownership, and there is our ownable.sol. And if we open it, we can see that it has this address public owner. In the constructor, it records that owner based on msg.sender. And it defines also the modifier only owner that require the msg.sender to be the owner and then calls the code of the function we apply that modifier to. It has a few additional functionality like the possibility for the contract owner to renounce their ownership or to transfer ownership to another user. But otherwise, it's pretty identical to what we had. And we'll talk about events later on. So now that we have that, we can actually remove all the functions that and the variables that we added for that purpose. So here we can remove the address owner. The modifier is also defined in the super contract. We can remove this from the constructor. And for the other two functions, the publish and the close function, we can just keep using the only owner modifier that's used, that's declared in ownable.sol. Note, by the way, that the simple fact of extending the ownable contract with our series contract is enough to make sure that the ownable constructor will be called before the series constructor when we instantiate our contract. Okay, our contract is taking shape. Now, the next thing we're going to do is add a few mutable state variables. And those mutable state variables will be used to maintain its business state. Note that you might have heard that the blockchain is immutable, which might be confusing since we said we were going to introduce some mutable variables. But you have to understand that what's immutable in a blockchain is its own state, its own data. The history of all transactions, basically. But nothing prevents those transactions to change the state of a contract instance. Simply, once it happens, nobody can deny that it happened, when it happened, and who made it happen. So, now, what are these mutable variables that we are going to need? First, there's one that we don't need to declare, and that's the balance of the contract itself in Ether. You have to remember that a contract works just like any account. It can store value, so you can send Ether to it, and the contract can send its own Ether to other accounts or contracts. And this is all handled for us. What is not handled for us, though, is the amounts in the contract contributed by each supporter. And we need to keep track of that to properly check the balance of each supporter's pledge on publication time. And also to implement the withdraw and close functionalities. So to keep track of that, let's create a variable called pledges that maps addresses to balances. And to do that, we just declare a new variable of type mapping between parentheses address equals superior uint. It will be public and called pledges. So in Solidity, a mapping is some sort of an associative array, an associative array that maps values to keys. But contrary to the other associative arrays that you might be used to, there is no way to know which keys have a value. By default, every key is associated to 0 in this case. And by declaring it public, we ask the compiler to generate a public getter that takes an address and returns a uint. And as we said before, we will record this pledge amount. So in the mapping values, we'll have amounts in way, so in the smallest denomination of Ether. Again, 1 way equals 10 to the minus 18 Ether. So, since there is no way to know which accounts have pledged some money just by looking at this mapping, we'll also need to keep track of a list of pledgers in an array of addresses. So to do that, address, that's an array of address, and this one will not be public, and it will be called pledgers. Next, since we need to make sure that the show creator cannot publish 2 episodes less than minimum publication period blocks apart, we need to keep track of the last block on which an episode was published, if any. And this will be done with a uint again. We'll make it public and call it last publication block. And finally, we'll store a list of published episode links, and each episode will have an unsigned integer identifier. And again, we'll use a mapping for that from uint to string public, and we'll call it published episodes. And since again there is no way to list assign keys in a mapping, we will increment the identifier each time we add an episode and keep track of the current value. So let's declare a new variable called episode counter. So with that, published episodes 1 contains the link of the first episode, and published episodes episode counter contains the link to the last episode that was published. And that's it for the mutable state variables that our contract will keep track of. Again, note that state variables declared as public have a public getter generated by the compiler, but none of those variables has a setter yet. So there will be no way to modify their value other than through the 4 methods we will implement now, being pledge, withdraw, publish, and close. So let's start with the implementation of pledge. First off, we need to verify a couple of preconditions. First, the pledge function will be called to add some money into the supporter's pledge the first time, and then to increase it every time. When we increase that balance, it doesn't make any sense to have a balance that's less than pledge per episode. And the first time a supporter pledges, he must pledge at least enough for 1 episode. Now, to access the value that the pledger sends with this transaction, when he calls this function, we can use the special msg.value variable. And then pledges at msg.sender will be 0 at the beginning when the supporter pledges for the first time. So we want to make sure that the sum of those 2 values, the existing pledge and the one that is added by the function, is greater than or equal to pledge per episode. Otherwise, we'll need to throw an exception. And note that when a Solidity function throws an exception, the state of the contract is completely reverted to. So the way we'll represent that precondition check is again with a require instruction. And what we require is that pledges for msg.sender plus msg.value, that's the ether value associated with the transaction used to call that function, is greater than or equal to pledge per episode. And we can add also a second parameter to the require, which is an error message. Pledge must be greater than pledge per episode, for example. Pledge here meaning the total pledge. Okay. The other thing that we need to check, we also want to forbid the show creator to pledge for his own show, which we can do by checking that msg.sender is not the same as owner, owner being recorded in ownable. So quite simply, we can do require msg.sender not equal owner. And then we have owner cannot pledge on its own series. Okay, so those are the two preconditions that we need to check. Now, there's just one small problem with that implementation. In the EVM, so in the Ethereum virtual machine, unsigned integers are represented on 256 bits, which means that they can have a value between 0 and 2 to the power of 256 minus 1. That's a very large range. But when you had two large values like that, there's always a risk of overflow. In other words, we cannot trust the value of a plus b if it's smaller than a, which will happen if a plus b is greater than 2 to the power of 256. This kind of overflow is very common in Solidity contracts. So OpenZeppelin, the library that we already used for the ownable contract, also published the SafeMath library that we can reuse. It was already installed earlier when into node modules when we installed the ownable contract. So all we need to do is import it and use it. So we can go back at the top of the contract and write import. We'll just copy paste the first part. Well, actually, let's write it down. OpenZeppelin Solidity /contracts /math /SafeMath.sol. And then to use it, given that it's a library and not a contract we can extend, we'll add the following line at the beginning of our contract. So right after the contract declaration, we can say using SafeMath for uint. And this basically extends the uint type with all the methods defined in the SafeMath library so that we can call them like we'll show you in a second. So with this declaration in place, we can change the lines, the first two lines of pledge. So here, instead of checking just the simple sum, we'll use the add function defined in the SafeMath library. And this returns the sum of both. And this will check for overflow and throw an exception if there is an overflow. Okay? And we will reuse the same kind of methods throughout the contract. Next thing we need to do in this function is to update the pledgers array. But before adding the function caller to the pledgers array, we need to verify that it's not already there. And since Solidity arrays don't have a contains method, we have to loop over it, basically. So let's create a new local variable called old pledger and initialize it to false. And then we can go over indexes from 0 to pledgers.length that we have. I++. And in there, we check if pledgers I equals msg.sender. Again, this contains the address of the account that is calling the pledge function. Then old pledger is true, meaning we found the sender in the pledgers array, so we can stop iterating. And then only if the pledger is not already, in the msg.sender is not already in the pledgers array, we can call pledgers.push msg.sender. And last but not least, let's increase the pledge for this pledger. And to do that, we can simply call pledges for msg.sender. and say this is the sum of the existing pledge plus msg.value. And again, we want to protect ourselves against overflow, so we're going to use SafeMath functions for that. So msg.sender.add msg.value. And that's it for the pledge function for now. Now let's move on to the withdraw implementation. So again, as a protection mechanism for supporters and an incentive mechanism to encourage the show creator to publish good content regularly, supporters should be able to withdraw their remaining pledge at any time. Let's say pledge for 10 episodes in advance, and after the second one got published, I'm not satisfied with the quality of the show. I can easily withdraw the 8 episodes worth of pledge I still have in the contract. I will still have paid for the first 2 ones, and I will still be recorded as a former pledger, but I won't participate in the funding of the show until I increase my pledge again. And the implementation for this withdraw functionality is pretty straightforward. First of all, let's retrieve the amount of my existing pledge. uint amount equals pledges for msg.sender. And as always, msg.sender gives us the address of the account that signed the transaction that called the withdraw function. Then, only if the amount of that pledge is strictly positive, do we want to go on and reset the pledge to 0 and transfer the amount back to the pledger. So, if amount is positive, strictly greater than 0, then pledges for msg.sender equals 0, and then msg.sender.transfer amount. Now the transfer function on the address type transfers cryptocurrency from the contract where it's called, so here our series instance, to the address it is called on, in this case msg.sender. And the amount that is transferred is specified as a parameter. So here it's amount. If the sending account doesn't have enough cryptocurrency to cover that amount, the function will throw an exception, which will return the state of the contract to what it was before withdraw was called. So in particular, if transfer fails, pledges for msg.sender will come back to the value it had before. Note that this should never happen though, because there are only 2 ways money can leave the contract, with withdraw here, and with the close function we will implement later. And the way the contract is implemented, the sum of all pledges will always equal the balance of the contract itself. Note that it's best practice to always update your contract variables before you call the transfer function to avoid reentrancy bugs. I won't go into details into those here, but keep that in mind. And that's it for the withdraw function. Now the next step is to implement the function called by the show creator when he wants to publish a new episode. The only parameter he has to provide is the link to the episode. So first off, let's check our preconditions. And there's only one in that case. We just want to check that last publication block is either 0, because that's the default value, or that block.number, that's a special variable that contains the number of the block inside of which this transaction will be mined, is greater than last publication block dot add. Again, we use SafeMath functions to protect against overflow. Minimum publication period. And here the error message will be owner cannot publish again so soon. So again, this require checks that the caller is not trying to call the publish method too soon after he called it last. Of course, that is if it was already called before. So if not, last publication block will still have its default value of 0 and require will pass. Note that in theory, it would be possible for the publish method to have been called on block number 0, but it is so unlikely that we are discarding this possibility because block number 0 is the genesis block. And in the genesis block, normally we don't call functions on contracts. Anyway. Then we use the special variable called block.number that gives us the number of the block containing the transaction where our function is getting called. In other words, it's like a now counted in number of blocks. And we compare that value with the mathematically safe addition of last publication block plus minimum publication period. In other words, we are checking that now is after last publication block plus minimum publication period. And since we are adding two unsigned integers together, there's always a risk of overflow, which we protect against by using the SafeMath add operation. An exception is thrown with an error message. Next up, let's update our contract state in the form of last publication block, episode counter, and published episode. So last publication block must be equal to block.number. Then we increase episode counter, and we use that to update published episodes for episode counter, and that will be the value of episode link. Nothing fancy about that, pretty straightforward. Now the next part is just a little bit more interesting. We need to subtract pledge per episode from every pledge that is large enough to cover for it, and add that amount to an episode pay local variable we will use later. So let's declare a local variable called episode pay equals 0. Then we go over all the pledges. So uint I from 0 to pledgers.length I plus plus, and then pledges for pledgers for I equals pledges for pledgers dot for I dot sub. So sub is just subtract in SafeMath, and we remove pledge per episode only if it's greater than pledge per episode. So we need to check for that first. So if pledges for pledgers for I is greater than pledge per episode, actually is greater than or equal to, then we can update it, and we can also add this episode pay equals episode pay dot add pledge per episode. And again, we use the SafeMath sub method here to protect again underflow in that case, which should never happen normally, given that we test everything first, but it doesn't hurt. Note that we use the pledges array to know which pledgers already called the pledge function at least once in the past. And if they did, and if they called withdraw afterwards, then we check the value of their pledge and update it if it can be. We also increase episode pay by that amount in the same loop, again using SafeMath add function for overflow protection. And last but not least, now that we know how much we should pay the show creator, we can actually do it. So the last line would be owner.transfer episode pay. And again, owner is recorded by the ownable supercontract in its constructor. So we transfer episode pay in way from the contract account to the owner, provided that there is still episode pay way in the contract balance. Otherwise, an exception will be thrown. But that, again, should not happen. So again, make sure that the full implementation matches this. And especially be careful about the comparison signs. And last but not least, let's look at implementing the close operation. So the close operation can only be called by the show creator, and it is used to stop all possible contributions, give their money back to all the supporters, and deactivate the contract instance. This last aspect is particularly important in smart contracts because smart contract code is part of the blockchain state, meaning a smart contract cannot be modified in place once it's been deployed. It's part of the contract you have with your users. So if you want to fix a bug or add a feature to your contract, your only option is to deploy another version of it on another address, to send your users to the new address, and to deactivate the old contract. Now, to deactivate a smart contract instance, you can call the self-destruct function on it. And that function takes an address parameter that makes it possible to redirect any remaining funds in the contract to this address. In our case, once we have paid back all the pledgers, there should be nothing left in the contract balance. So the implementation of this function is pretty straightforward. Again, the sender has already been checked by the onlyOwner modifier. So now all we need to do is to iterate over the pledgers array again. 0 I less than pledgers dot length I plus plus. So we load the amount of that pledge, pledgers dot for I, and if amount is greater than 0, then we call pledgers I dot transfer amount. So we iterate over the pledgers array, and if any of them still has a positive pledge, we just pay it back to them. And then once this is done, we can call the self-destruct function and pass it, for example, the address of the owner. So any possible remaining fund will be paid to the owner of the contract. And in our case, it should be 0. Note that we don't need to reset pledges because when we call self-destruct, all state variables are reset anyway. This saves us some gas when calling this already expensive function. Indeed, if there are a lot of pledgers with a positive pledge, this function could cost a lot because each call to transfer will cost 21,000 gas. And if all the transfers go smoothly, the balance of the contract should be 0 when self-destruct gets called, so owner should get nothing. And after the call to self-destruct, the contract is disabled, meaning that any further call to any of its functions will throw an exception and all its state variables will be reset. Now we have implemented our 4 transactional functions. Let's move on to what we call view function. Now, one last general note about all of these transactional functions. Calling each of these functions require a transaction to be sent to the network, mined into a block, and synced back with all the nodes in order to be considered as processed. So each one of these functions is asynchronous in nature and does not return any value, because there is no way for now to retrieve the return values of such functions in the EVM anyway. The only functions that can return values are either view or pure functions. View functions are functions that can read the state of the contract but not modify it. And pure functions are functions that don't access the state of the contract in any way, either to modify or to read it. Those are typically utility functions that simply perform a calculation on parameters and return the result, for example. Note that transferring money to another account or contract, calling self-destruct, or doing anything that affects the blockchain state in such a way that it has an effect that needs to be synced with all the nodes in the network is considered modifying the state and requires a transaction. But view and pure functions don't require a transaction. That being said, all the getters generated by the compiler for public state variables in our contract will be view functions. And we are going to add a couple of view functions of our own to get more insight into the state of the contract. The first one will give us the total number of pledgers that already called the pledge function. Note that pledgers itself is not declared as public, as you can see here. But we are still interested in knowing how many people supported the show at some point, and we will later call them followers. So after the last function, let's add a new function called total pledgers, which won't take any parameter, will be public, will be marked as a view function, and this one returns a uint, and it will simply return pledgers dot length. So as you can see, we mark that function as a view function, it's public, and it returns an unsigned integer. The next view function will return the number of pledgers whose pledge is still greater than pledge per episode. Those are the pledgers who will participate in the funding of the next episode at this point in time. Of course, unless they call withdraw before the next episode is published. So let's create this function called active pledgers. Again, it's public, it's a view function. It will return a uint. Uint active equals 0, that's a local variable. Then we iterate over our pledgers array. And there, if pledges for pledgers for I is greater than or equal to pledge per episode, then active plus plus. And then at the end of this for loop, we can return active. So as you can see in this function, we don't modify any state on the contract, we just query it. So again, this function is a public view function. It returns an unsigned integer and it increments a number of active supporters by going over all the pledgers and checking the balance of their pledge to see if it's greater than or equal to pledge per episode. And the last view function will give us some visibility into how much the show creator can expect to be paid for next episode, provided again that no supporter withdraws that pledge before that. So let's create another view function called next episode pay. Public view returns uint. Uint episode pay equals 0. And again, for uint I equals 0 until I, so long as I is less than pledgers dot length I plus plus. If pledgers I is greater than or equal to pledge per episode, then episode pay equals episode pay dot add pledge per episode. And we return episode pay. So as you can see, this function implementation is similar to the loop we have in the publish function implementation, but we decided not to call this function there to avoid looping over the pledgers array twice. And that's it for the first version of our contract. So again, make sure that if you're following along, make sure that your version corresponds exactly to this. And as you can see, in just a little over 100 lines of code, we implemented a simple decentralized version of Patreon. Not too shabby. Now, before deploying our contract, we need to fix a small problem with the migrations contract. So if you remember, let's go over there. Now, if you remember, the migrations contract was downloaded with the Webpack box. And as we warned you then, the box you're unboxing doesn't know which version of Truffle and Solidity compiler you're using. In this case, the code of the migration contract still uses the old syntax for constructor, being a function with the same name as the contract. And if we don't change that, the compiler will warn us later, so let's update this constructor. First of all, we'll use the same version of Solidity as in our contract, so 0422, for example, for the pragma. And here, we'll just change that from function to constructor, remove the name, and that's it. And as you can see, all this contract does is maintain a last underscore completed underscore migration state variable, and this is updated by Truffle itself after running each migration script. Speaking of migration scripts, let's create one for our series contract. So under the migrations directory, we will create a new file and call it to underscore migrate underscore series.js. And the to underscore prefix will make sure it runs after the one underscore initial underscore migration.js script that deploys the migrations contract. So in this new file, let's start by loading the series contract, which we do by using the artifacts.require function provided by Truffle. So var series equals artifacts.require Series.sol. And of course, Truffle will load that from the contracts directory. Then, just like in the migration script for the migrations contract, we need to export a function that takes a special deployer object provided by Truffle. So module.exports equals function that takes the deployer object, and that's it. And then we can call a deploy function on that deployer object. So deployer.deploy, and that deploy function takes a couple of parameters. The first one is the series object that we loaded with artifacts.require. And then we can add all the parameters that we want to pass into the constructor. So in our case, that will be the title of the show. Let's set it to proof of cast, for example. And then we need to pass the pledge per episode and the number of blocks between two episodes. So again, all of these parameters correspond to an amount in way. So we can use the Web3 library that's also injected by Truffle to convert an ether amount into a way amount and avoid any possible calculation error. So in our case, for example, we'll decide that pledge per episode is 0.005 ether, which corresponds to about 2 euros. And this is how the two-way function works. So we specify the amount in ether and the name of the originating unit. Okay, and then we need to specify the number of blocks between two episodes, the minimum number of blocks between two episodes. So here we'll say that we publish a new episode every 2 weeks, so that's 14 days times 24 hours times 60 minutes times 60 seconds. And in the production main network, blocks come every 15 seconds, so let's divide this by 15. Okay, so that says that we have to wait at least about 2 weeks between two episodes. Okay, so don't forget to save all our files. And now let's try to deploy our contracts. So make sure that Ganache is running in the background. For us it is. So again, Ganache starts with 10 accounts, and in each account there is 100 Ether. And if we go back to the transaction list, we see that the transaction list is empty. But if we go to blocks, we can see that we are actually at block number 8,000 and so on. This is because new blocks were mined every second, even without any transaction. Now let's go back to the transaction list, go back to the terminal, and run the following command: truffle migrate -- compile all -- reset -- network Ganache. So the compile all parameter forces the compiler to recompile all contracts, even if it still sees an old version already in its cache. The reset parameter tells Truffle to ignore the previous state of the migrations contract and to redeploy everything no matter what. And finally, the network parameter specifies which network truffles should deploy everything to. So let's run this command. Hopefully we didn't make any mistake in the contract. And we did. Yes, there is a syntax error here, just a little typo. So we need to go to Series.sol, line 62. Let's go back here, Series.sol, line 62. And sure enough, we forgot an S here. Now we save the contract again, we go back to the terminal, and we run the truffle migrate command again. And this time compilation is okay, and we can see a certain number of transactions happening. So this is a transaction hash, this is another one. So as you can see, we have 4 transactions that happened here. The first transaction is the one that deploys the migration contract. The second one updates the state of the migration contract to keep track of the fact that the first migration script was run. Then we run the migrate series script, and again we update the state of the migration contract to to keep track of that as well. So as we can see here, we have 4 transactions that we should be able to see indeed in the transaction list in Ganache. So again, first transaction is contract creation, that's for migrations, and the third one is for the series contract creation. Of course, the addresses and the hashes will be different for you because they are random, but you see how it works. And based on that, we can see that our series instance contract is now available at this address, 0x6b, and so on. By the way, this is the encoded code of our contract, and this is the address at which our contract is available on our own little development blockchain here. And just like that, we implemented our contract and we deployed it to our development network. You can congratulate yourself. Now there's one more thing I want to show you before we move on to implementing the web interface for our contract. As I said before, every transactional method is asynchronous and takes at least 15 seconds to process a call on the main Ethereum network and see the results. For that reason, it would be really helpful to be able to be notified when something changes in our contract state. And in Ethereum, we can use a special mechanism to do that called events. So let's go back to Atom. So we can declare different sorts of events in our contracts, along with the data that they can carry along. We can emit those events from our transactional functions, and on the client side, we can watch our contract instance for those events to run special functions when they are emitted. So first, let's declare a bunch of events in our contract. So I'm going to go just above the above the constructor, and I will declare a first event type called new pledger, and it will take just one field, address of the pledger. Second event will be new pledge, and it will have an address that will be indexed. I'll explain what this means in a second, as well as the pledge and the total pledge. All that is information that can be retrieved by the watcher of these events, and that can be useful to them. So new publication, uint episode ID, string episode link, and uint episode pay. And then we'll have an event to signal withdrawal. Oops, withdrawal. Yeah. This will be address indexed ledger, uint pledge. Then we'll have an event called pledge insufficient, address indexed ledger, uint pledge, and last but not least, an event for signaling when the series is closed, uint balance before close. Okay, so an event declaration starts with the event keyword, then the name of the event, and then between parentheses the different fields that we want to pass with each event, along with their type. Notice that certain fields, certain events have indexed fields, and indexed fields can be used on the client side to get notified only for events that have certain values of those fields. So for example, I could watch for pledge insufficient events only when I am the pledger. So again, we declared 6 types of events. New pledger can be interesting for the show creator. New pledge can be interesting for the show creator and for the pledger himself to know when his pledge was recorded. New publication can be interesting for all active supporters. Withdrawal can be interesting to the show creator and for the pledger himself to know when his withdrawal was processed. Pledge insufficient is particularly interesting for pledgers to know when their pledge goes under the pledge per episode level, to let them know they should increase their pledge again if they want to keep supporting the show. And finally, series close just notifies all pledgers that the contract was deactivated. Now let's modify our 4 transactional methods to emit some events. We can go back to pledge, and in pledge there are 2 locations where we need to add something. So when we add a new pledger, we can emit new pledger, and we pass msg.sender because it takes just one argument, and that is the pledger, which you can see here. Okay. And then at the end of the function, we can also emit new pledge of msg.sender for msg.value and pledges for msg.sender. So this new pledge event again takes 3 fields. The first one is the pledger itself, second one is the pledge they just added, and last one is the total pledge. And this is exactly what we are passing here. That's it for the pledge function. Now let's have a look at withdraw. And here, there are actually two events that we need to emit. The first one is withdraw. And it takes two arguments, msg.sender and amount. That is the amount of the pledge before we reset it. And also, since when you withdraw, you mandatorily go under the level of pledge per episode, we also need to emit pledge insufficient. msg.sender, and the new balance is 0. Okay, now we can modify the publish implementation as well. Here, if the pledge of the pledger's I was greater than pledge per episode, we decreased it by pledge per episode, but then it means that it might have gone under the level. And we need to check for that. So if pledges for pledgers for I, the new value, once it's been updated, is less than pledge per episode, then we need to emit the pledge insufficient event for pledgers I, and the current pledge is pledges the pledgers dot I. And of course, after the transfer is done, we also need to emit new publication. So the ID of the new publication is episode counter. Its link is episode link. And episode pay is the amount that the creator got for that episode. And last, in close itself, before calling self-destruct, let's just emit series closed. And we just need to keep track of what the contract balance was before we actually close the series. That could be interesting. So uint contract balance, we need to add that at the beginning of the function because then everything is updated. And we can do this with address of this dot balance. So again, the address type has a balance field that gives its own balance. And we can get the balance of the current contract with this. So events are emitted when the block containing the transaction that emitted them is mined. They are added to a special region of the blockchain state that we call the logs. And you can watch those logs for new entries. And we'll show you how to do that later on when we work on the web interface. So with that, we can save our contract, go back to the terminal, run the Truffle command again to migrate everything, to recompile and remigrate everything. And we see that compilation failed. Yeah, because we made a typo again. So we need to go to series line 23. Address indexed pledger. Yeah, that's where the typo is. I save, I go back, I run the Truffle migrate command again. And that's it. Notice that the address at which our contract was deployed, which we can see here now, is a new one. The old one is still there, and it's accessible at the old address, and we should let our users know that it's going to be deactivated, and then deactivate it ourselves. Now that our contract is deployed, we can start working on the web interface for it. Now, usually when you have a first version of a contract like that, you can try to interact with it in a terminal console using the Truffle console. But that's rather boring, so let's jump right into developing a web interface for our smart contract. Now, this web application will show details about the show and adapt its user interface to the user that's connected to the page. as well as to the state the contract is in. And as explained before, our web page, and more specifically the JavaScript part of it, will discuss with the Ethereum node and the smart contract through the Web3 JavaScript library and the MetaMask browser extension. So let's start by having a look at what the default web interface generated by the Webpack box looks like. To do that, just in the terminal, you can launch the command npm run dev, again from within the project directory. So this will run the Webpack dev server locally and use files in the app directory as a source. And also watches for any changes on those files so that you can see the result of your changes automatically in your browser without having to reload the page. So right now in the terminal, you will see a message like this one. So we have an error in app.js, module not found, can't resolve, metacoin.json. So it's looking for metacoin.json and it can't find it. And indeed, since we removed the metacoin contract without adapting app.js yet, the script is a little confused. We'll fix that in a moment, but this shouldn't prevent us from loading the page on this address. That's right here, HTTP localhost 8080. So we can go to the browser and load that in a new tab. And that's the default interface for the metacoin contract. Again, it's a sample web page. And if you open the browser console, which you can do by right-clicking in the page and then clicking Inspect, and the console tab. By the way, I strongly advise you to always have this console open when you're working on your web interface, because that's where you will see the errors in app.js. And you can see the same kind of mistakes, the same kind of errors that we have on the console. So let's get rid of these errors first. Let's go back to Atom and open app/javascript/app.js. So here, instead of importing metacoin artifacts, let's import series artifacts from series.json. Now you might wonder what this JSON file is. What you didn't see is that earlier on when we launched the Truffle migrate command, the compiler did its thing and it stored a certain amount of information inside the build/contracts/series.json. And this JSON object actually contains all the information concerning the API of our contract, so all the functions that can be called, the parameters it takes, and so on, as well as the source code, the bytecode, that is the compiled version, and also at the very end of the file, which is a big file, something that's important, we have the address of our contract as it was deployed to our network with identifier 5591 in our case, and that's the network ID for Ganache. So when it was deployed to Ganache, this was the last address of this contract. So this file is pretty important, and we need all this metadata in order to load the contract in our web interface. So again, we import series artifact from build/contract/series.json. And then in the next line, we'll create a new Truffle contract abstraction. So let's call it series instead of metacoin. And we use series artifacts that we just initialized before. So these two lines, they transform the metadata produced by the Solidity compiler inside of build/contract/series.json into a Truffle contract abstraction object that makes it easier to interact with our contracts later using JavaScript promises. And the last element to modify is the start function. So here we have a start function and it sets a provider on metacoin. So instead we should set the provider on the series contract. So as you can see, the app.js scripts create an app object attached to the window object and defines a certain number of functions and properties on that object. And the start function is triggered at the bottom of app.js when the document is finished loading. So here we have a window.addEventListener. That's just standard JavaScript. When it's loaded, we call app.start at the end. So what this part also does is try to determine whether MetaMask is installed in the browser or not. If it's installed and ready, it will have injected a Web3 object into the window object. That's an instance of the web3.js library main class. If that's the case, then we extract its current provider, which is some sort of a connector, and we instantiate a new Web3 object using that connector. This way, we use the version of web3.js declared in package.json. So here we have dependency, dev dependency web3 in version 0.20. Instead of the version loaded in the browser by MetaMask. So MetaMask originally works with its own version of Web3, but we have no control over that. So we just use the connector inside that object and inject it into our own Web3 instance. Now, if MetaMask is not available, there is no Web3 object on the window object, then we try to create our own Web3 instance and to connect it directly to our local node using an HTTP provider. And here the script is assuming that our node is running on port 9545, which is not the case, so we can fix that line by just changing the port number to 7545. That's the port on which our Ganache node is running. Let's delete this console warn instruction right here. It's not needed anymore. Now we save app.js and we can go back to the browser. And you can see that refresh balance still complains about the absence of MetaCoin. MetaCoin is not defined. So you can delete the refresh balance in function in the app object. So this is not useful anymore. This is MetaCoin specific. You can also delete the sendCoin function, by the way. Same thing. Not needed anymore. We won't need the setStatus function, so you can remove that as well. So now we only have the start function, and we can remove the last call to refresh balance that doesn't exist anymore. We save, we go back to the page, the interface is reloaded, but this time we don't have any error in the console anymore. But of course, the interface itself is still related to MetaCoin, and to fix that, we'll need to have a look at index.html. So let's go back to Atom, load app/index.html, and we can clear everything between the body opening and closing tags. Okay, so now the interface is clean. And if we save, we go back to the browser and the page is blank. Now, what we will do is we will integrate the Twitter Bootstrap library, which will help us have some basic design and make our app look a little nicer. To do that, we can go to getbootstrap.com to getting started. And at the top there, you will find the following line to be copied. That's the CSS line. So we just copy that. Well, actually, let's just hit the copy button. And here, right after the previous link instruction or tag, let's paste that one. And there we just imported the CSS style sheet for Bootstrap from a CDN. Now let's go back to get Bootstrap, and we also have a couple of lines to copy for the JavaScript part. So let's not use the jQuery Slim version that's here. We'll just copy like those two last lines to import the popper and the Bootstrap libraries, JavaScript. And we'll do that at the end of the body tag. So now this is what our file looks like. And again, we are not copying the first line because we are going to require a fuller version of jQuery. And to import the right version of jQuery, you can go to code.jquery.com. And here you will see we'll use the jQuery 3 version, and we just need the minified one. And here it gives you like the script that you can copy and paste it here. And the last thing we do is take the last script instruction from the header, and we move that after the 3 other scripts. So with that, we are importing the style sheet for Twitter Bootstrap, and then the 4 scripts, so one for jQuery min, the other one for popper min, and the third one for Bootstrap min, and finally our app.js. Okay, then let's just change the title of the page to remove the last MetaCoin reference, crypto series, for example. And last but not least, let's go to style sheets, app.css, and we remove all the selectors except for the first one, the body one. And in here, instead of having a margin top of 10%, we'll just define a margin top of 30 pixels. Let's go back to the browser. As you can see, it's reloading. Title is crypto series. We don't have any error in the console. That's it. So everything is in place. We can start creating our basic user interface for crypto series. So our user interface will basically be one big card, showing the details of the show in several sections. And the title of the show will be in the header of the card. And the footer will contain certain buttons for creator-specific actions like publish and close. So let's go back to index.html. And at the beginning of the body tag, we'll add div class of card. Okay. And then in there, we'll have a div, the class of card header. And we want to center the text as well. And this will just contain an H1 with a span, ID equals title. This will be useful to reference this span from within the JavaScript later. Close the span, close the H1, and that's it. That's the card header. Okay, next div ID equals owner footer. Again, ID will be useful to access this element later on, and it will be a card footer. With the text muted. And in that footer, we'll have 3 elements. We'll have a button called close button with a class of btn danger because we want it to appear as red. And this one will be aligned to the left of the footer. And text will simply be closed. We also want to have another button called publish button with a class of btn. btn success to make it green. And this one will float on the right side. And the text will simply be publish. And we'll also add another element that is a span with ID publish wait, and this will contain a message to indicate that the number of blocks that the creator has to wait before he can publish a new episode, if any. Style equals margin right. That's just to add like a little space between it and the button. And for now, this span doesn't contain anything. Okay, we can save this file, go back to the page, and we can see that we have a card with our title and with our footer and our 2 buttons. Now that we have that, let's try and set up the basic infrastructure to load the title of the show from our contract in app.js. So let's have a look at the start function again. And as you can see, the end of this function calls the get account, asynchronous method provided by Web3 on its ETH subobject. This Web3 method doesn't use JavaScript promises, but a more traditional error data callback mechanism. So we just pass a function to it. That's this function right there. That checks if there was an error in loading the accounts and otherwise initializes 2 global variables called accounts and account. What's important is that when MetaMask is configured, enabled and unlocked, this list of accounts will contain only one account, the one that is currently selected in MetaMask. Otherwise, this list will be empty and we can warn the user about that. So let's create a new function that will refresh the interface of the page once accounts have been loaded. And for that, it's important to wait for accounts to be loaded because soon we'll add a function to refresh the account-specific part of the contract data. For now, below the start function, let's add a new field to the app object in the form of the refresh contract data function. So refresh contract data colon function that doesn't take any parameter, and we'll declare this function now. So here we'll declare a local variable called series, and then series.deployed. I'll explain what this means in a minute. Then function instance. So in this refresh contract data function, we define a variable to hold an instance of the Truffle contract object. We'll need to call functions on it. This variable will be initialized asynchronously by requesting it from the Truffle contract object. So that's the series variable here that was initialized here. And on it, we call the deployed function. And that deployed function returns a JavaScript promise. And when that promise resolves, then we can get access to the instance. And we save that into the series local variable. And once we have that, we can chain another promise by returning series.title. So return series.title. So we, in fact, call the title function. And because we are interacting with a Truffle contract abstraction, this title function is mapped onto the contract itself and returns another promise. So we can then function title. We can chain another then block. And in this function, we'll get access to the title returned by this function. So if you remember correctly, title is one of these public view getters generated by the compiler because we declare title as a public state variable. So it does not require any transaction. But still, in Truffle contract, any call to a contract function is asynchronous. And once we have the title, we can use jQuery to set it as a content on the span whose ID is title in the HTML page. And to do that, we'll just use the $title.html title. Now you can save this. Make sure that index.html is saved as well. And that, again, Ganache is running in the background. And we have our contracts deployed. Now let's go back to the browser, reload the page. And here we don't see the address. And that's because we didn't install MetaMask yet. So to install MetaMask, let's go to metamask.io. And since we are using Chrome, and I strongly advise you to use Chrome because there's also a Firefox and Opera version, but the Chrome one is probably the most maintained. So here I can just add this to Chrome, add the extension, and now I have a little fox in my plugin bar here. You can close this website, close the Chrome Web Store, MetaMask, jQuery. And when you click that fox, you have the procedure to initialize MetaMask. So again, MetaMask is a plugin that transforms your Chrome browser or your web browser into a dApp browser, meaning that it contains all the functionalities to manage your wallet, so that your set of cryptographic addresses and connections to various Ethereum networks. So terms of use, we'll accept. We need to scroll down and accept. MetaMask is beta software, accept. Scroll down and accept. And then we can create a new vault. So the way that MetaMask keeps track and keeps our cryptographic keys secured is inside a secured vault. And to do that, we'll just initialize a new vault. So we set a password for that vault. It gives us like a series of words that you should keep to secure your vault, because the only way to restore your vault in case you lose your laptop, for example, or in case your extension gets uninstalled or whatever, is with this list of words. So you should keep them in a secured place, like a password manager, for example. I've copied it somewhere safe, and by default it creates a new account. Now, just to give you a little overview of the MetaMask interface, on the bottom left, on the top left, you have the list of networks that MetaMask can connect to, and we can define our own. I'll show that in a minute. Then in the upper right corner, you have the list of accounts, and you can create new ones or import ones. And again, we'll do that in a second. And finally, you have the menu with the settings. So here, the first thing we'll do is go to the network list, select custom RPC. And here in the RPC URL, we'll define HTTP localhost 7545. That's the address of our Ganache node. We hit save, and then we go back. So now we are connected to our private network, our Ganache node. Okay, so thanks to that, to the fact that we installed the MetaMask extension in the Chrome browser, now we have a Web3 object that's injected into the page. And if we reload this page, it will say that we are now using the Web3 detected from external source, and we still don't see the title of the contract updated, and that is because we are not actually calling the function that we just defined. So this refresh contract data function, we are not calling it from anywhere. So as the last line of the start function, you can call app.refresh contract data and save app.js. And now we can see the title of our contract that appears as the title of our page. And this is the basic logic to be able to access all the information in our contract. So now I'm sure you can guess what we are going to be doing next. We'll just add more interface elements and then fill them in with data coming from the contract. Let's start by adding more information about the contract itself, mainly the delay between two episodes, both in number of blocks and an estimate in number of days. And also the pledge per episode, both in Ether and in euros, for example, because that's the currency that I'm used to. Let's go back to index.html first to add the interface bits. So right after the card header, we'll define a new div. Okay, now let's go back to, well, first to the browser to check that our interface looks as expected, and it does. Actually, it does not, because I used the wrong class here, text muted. Our page is reloaded automatically. And now the interface looks okay. Now let's go back to app.js to fill in that information. And to do that, we'll update the refresh contract data function in app.js to start filling those in. There, the game is simply to chain several promises together by returning the next promise from each then callback. So we already had the first one to return the series title. Then we set the title on the HTML. We can continue doing the same kind of things. So first, series.minimum publication period, which again is a public state variable on our contract. So it has this getter generated by the compiler, function minimum publication period, and we can just set it on the minimum publication period blocks, HTML. Since it's a number, we want to convert it, minimum publication period. And then we can also display it in a number of days. So that will be in, minimum publication period time dot HTML. And here we'll just do a little bit of calculation. So minimum publication period, we multiply that by 15 to have in seconds, and then we divide it by 3600, that's number of seconds in an hour, and we divide again by the number of hours in a day to get a number of days. And then we just add this days element. Okay, again, you can save, go back to the page, and we can see now that we defined our number of blocks between two episodes as 80,640, which corresponds to about 14 days. Now let's return series.pledge per episode. Same logic. Then function pledge per episode. And here we'll just, for now, set the pledge per episode ETH dot HTML. And here we just need to do a little conversion because pledge per episode is returned as an amount in way and we want to display it in Ether. And for that, again, we can use web3.fromWay this time. Earlier we used two-way. Pledge per episode in Ether. So here we're converting a way amount into an Ether amount. And again, you save, you go back to the interface, and you can see that the pledge per episode is 0.005 Ether. And to reassure people who don't have any notion of what Ether is worth, it would also be nice to set pledge per episode fiat to the value of the pledge per episode in a fiat currency. In this example code, I will go with euros because that's what I'm using, but I'll leave it to you as an exercise to change the currency or to set up some drop-down list where the user can choose which currency he wants to see. And to get the rates, we are going to use a simple API provided by CryptoCompare. So if you go to cryptocompare.com/API, you can see the documentation for the API we are going to use. Let's go back to app.js and show you how to do that. After this refresh contract data function, let's create a get ether price function. And this function will take two arguments, fiat and callback. So fiat will be the symbol for the unit, the fiat currency unit that we want to convert the Ether price into. And the callback will be a function that returns that asynchronously, because we are going to use the jQuery library to do a get JSON https min-api.cryptocompare.com/data/price, and then we can specify the fsim. So that's the cryptocurrency for which we want the price, ETH, and TSIMs, that's the target symbols. In our case, we'll just get it in US dollars and euro, for example, even though we only use the euro, but I'm giving you some help if you want to use US dollars instead. And this this call will return the data in a callback function, and in turn we can give that back to the caller by calling the callback function with data fiat, because this web service will actually return a JSON object with keys being the fiat currency symbols and values being the amounts. So you will see in a second how we call that function. So now in the previous one, in the refresh contract data function, after having set the Ether amount on the page, we can also now call app.getEtherPrice. We want the price of Ether in euros, so EUR. And then we pass a callback function that takes the price. And once we get this price, we can use jQuery again, pledge per episode fiat .html plus price multiplied by web3.fromWay, because again, the pledge per episode is returned as way, so we need to convert it just as before. Pledge per episode Ether. And actually this multiplication results, we want to convert it to two decimals. So suffix 2 plus the unit, that will be euro. We save app.js, we go back to the page, and after a few seconds you will see now that the price appears also in euro. So 0.005 Ether at the time of this recording is worth 2.14 euros. Now let's add a section for information about supporters of the show. Let's go back to index.html, same logic. We had this div show info. We'll create a new div, id equals supporters. Class is cardbody. And close this div. And that's it. So now we can save the file, go back to our web interface. We can see that the interface corresponds to what we want. Yes, so now we can go back to app.js to fill in that information. So still in refresh contract data. After this, we can return series dot active pledgers. That's our getter for the active pledgers state variable. So we can retrieve it in the then block. Active pledgers.html. Active pledgers. We can do the same for total pledgers. Return series.total pledgers. And then we can return series.nextEpisodePay to load that from the contract. So we get that in a new then block, function next episode pay. Remember that this is an unsigned integer amount in way. So we'll need to do some conversion here. First thing, we can display it as is in the next episode pay ETH span, HTML plus web3 dot fromway, next episode pay Ether. And then again, we can reuse the get ether price function that we declared before. Function price and once we get that price, we can set it on next episode pay fiat. And again, multiply price by the web3.fromWay next episode pay in Ether. Again, we convert that to be 2 fixed decimals plus euros. That's it. We can save app.js, go back to the interface. And now we can see that we have 0 active supporters, 0 followers, and the next episode pay will be 0 Ether, which corresponds to 0 euros. And everything is consistent. Now there's just 2 more things that we should add to this interface to cover our bases. First of all, we should add some elements to the user interface to let the user know when something is loading and the information he sees might not be up to date. For this, I'm just gonna use some code for a CSS spinner with a backdrop that I found on a website called MenuCool. Okay, you can probably find this code in a lot of different places. So I'll just copy this div id cover spin, and I'll paste that at the beginning of my body in index.html, right above the card. And then I copy this CSS and I paste it in app.css. I save everything. So now we have this cover spin that we can hide and show when there is progress. So this will be our universal progress indicator if you want. So for example, in app.js, if I go back to the beginning of refresh contract data, here I can do cover spin dot show to actually show that progress indicator. And then at the very end, when everything has been displayed, I can just call cover spin dot hide. Now if I go back to the page, whilst it's loading the information, you could see the progress indicator, and when it's done, the progress indicator is hidden. And then last thing I want to add is some error handling, because any contract function call could throw an exception if something is not right, and it would be good to know about it. And to do that, we can add a catch to our promise chain. So at the very end of this refresh contract data chain of thens, I can add a catch. That will take a function that takes an error, and then we can, for example, log that error to the browser console like this. And of course, even if there's an error, we want to hide the cover spin progress indicator. And with that, we are now ready to add some account-specific information to let the specific user connected through MetaMask where he's at. Now, the next thing we want to show is details about the user's support. How much he pledged, how many episodes does that fund, etc., etc. But of course, this information only makes sense if there is an account selected in MetaMask, meaning MetaMask's vault is unlocked, and if this account is not the one of the owner of the contract, aka the show creator. As a matter of fact, the same thing can be said of the footer of the card with the close and publish buttons. It only makes sense to display them if the connected account is the owner of the contract. But in order to see all of that in a browser, we need to import the accounts from Ganache into MetaMask. This way we will be able to switch from the owner account to any other account. And to do that, we can go to Ganache and go to the accounts list. And on the far right of every account, there is this key button. We can click that key button and it shows, of course, the address of the account and also the private key that we can copy. And then we can go back to the browser, open the MetaMask extension, the account menu in the upper right corner, and then we can import account. There we can choose a type, either private key or JSON file. We'll use the private key directly, and we can simply paste the private key here and type import. And as you can see, now it's connected to the private network with that account that's called account 2. And the balance is 99.582. And if I go back to Ganache, I can see that's 99.58 corresponds to the balance of this account. By the way, Ganache only shows the balance of accounts with 2 decimals. So it's an approximation. Here, let's edit this account to call it, for example, Ganache 1, to rename it, and that will be clearer for the end. And we can do that for a couple more accounts. So I go back to Ganache, copy the private key for the second account, done, go back to MetaMask, import account, private key, I paste the private key, import, and I rename it to Ganache 2. Let's do it for the third one. That should be enough. And that's it. And again, you can see that the balance here is 100 Ether. And now we can switch from one account to the other by simply going to this menu right here and clicking the right account. For example, here I selected the account that deployed the contract since it's the first one by default. Okay, refresh the page. And so here I should not see the supporters section because I'm the show creator, but I should still see the close and the publish buttons. Actually, see, yes, I should still see the supporters section because that's general information about the contract, but now we'll add a section that should only be visible to others than the contract creator. Let's add this to index.html. So below the supporters div, let's add yet another div with an ID of your support. So this will be user specific. And this div will have a class of card body. So in this section, we show the amount of the user's pledge in Ether and in fiat currency, in euros here. And we also show how many episodes that corresponds to. And finally, we show 2 buttons to either withdraw your pledge or increase it. You can go back to the page after having saved this to check the interface. That seems to correspond to what we wanted to do. We have our two buttons here. But then, of course, everything is visible. Now let's go back to app.js and declare a new function right after refresh account data, and we'll call it, refresh contract data, and we'll call it refresh account data. This will be a function, and this time it will take an argument, being the account for which we want to refresh data. Don't forget to add a comma here because those are fields in the app object. First off, let's check if an account is provided, and if so, show the progress spinner and load the contract instance and call the owner getter on it. So first of all, if undefined equals account or null. Okay, so if account is null or undefined, then we return. There's nothing to display here. Otherwise, we can start by showing the cover spin. Then, just as before, we declare a new local variable called series, and we call series.deployed. Then that takes a functions with an instance, and we use that to initialize the series local variable. And then we can return series.owner. That will be useful to identify what we do next. And then a function with the owner. And then we can do a test. So if account, so that's the account for which we want to refresh the interface, so that's the selected account in MetaMask, corresponds to the owner of the contract, then we'll call a function that we have not declared yet called refresh owner data. And we'll pass it the series object. Else, we'll call another function that we'll also declare in a second, refresh supporter data. And we'll also pass it the series object and the account for which we want to refresh the data. Of course, the series.owner function can still return throw an exception. So let's be careful here and handle errors to at least hide the progress indicator and log console.error. Now in a minute we need to declare refresh owner data and refresh supporter data. But first off, let's add a call to this function to the start function. So right after app.refresh contract data, we can actually I should have this should go here inside the callback, and now we can do app.refresh refresh account data, and we can pass it account. Okay, now of course we need to define those two functions that are called by refresh account data. So again, after refresh account data, let's declare a new function, a new member called refresh owner data. That will be a function that takes just the series object and does something with it, and also refresh supporter data and the account and does something with it. Now let's start with the refresh owner data declaration. First thing, we can hide and show the right sections. So support, sorry, I need to put this in quotes. So the your support section can be hidden because we are not a mere supporter, we are the show creator, and those withdraw and pledge function will be inaccessible to us anyway. And then we can do show the owner footer with the publish and the close button. Based on that, we can call series.episode counter. That's the getter for the episode counter. And the goal here is to determine whether an episode was already published before. And if episode counter still has its default value of 0, then that's not the case. Okay, so if episode counter dot toNumber equals 0, why toNumber? Because episode counter is an unsigned integer, and since unsigned integer are represented on 256 bits, which is way too big for a normal JavaScript number, it's represented in JavaScript as a special class called big number. And it's kind of hard to do this kind of calculations and comparison on big numbers. So we just convert it into a JavaScript number, knowing that episode counter is really unlikely to go over like the range of a JavaScript number. So if we have that, then we can use publish button. We can enable the publish button by setting its disabled property to false. And we can initialize the message of the publish wait span. We can set that to you can publish whenever you want. And then, of course, we can just hide the progress indicator at this point because we're done. Otherwise, we'll need more information. And what we would like to do is replace the message in the publish wait span with a message indicating how many blocks the creator still has to wait before he can publish a new episode. And to do that, we need to load a couple of elements from the contract. We need the last publication block number, so the block number on which the last episode was published. We also need the minimum publication period. And with all that, we need to do a certain number of calculations. So first of all, let's declare a couple of local variables. Last publication block number and minimum publication period number. Okay, and then we can use series last publication block. That's the getter for the last publication block state variable. Then function last publication block, again, that's returned as a big number. So we'll store it in the last publication block number as a number. Last publication block dot to number. Then we do another call on the contract, series.minimum publication period. And we get a function, minimum publication period. And again, minimum publication period number equals minimum publication period dot to number. Okay, so now we loaded both elements from the contract. Now we need to determine what is the current block number on the node on the blockchain that we are connected to. And to do that, we can use a Web3 function, web3.eth.get block number. And again, this does not use, Web3 doesn't use JavaScript promises yet, but instead it uses mere callbacks that takes an error and our block number. And in this callback, we can finally do our check. So if last publication block number plus minimum publication period number is greater than block number, it means that we are currently before the soonest date when we can publish a new episode. So that means that the message in publish wait must state that fact. So you have to wait for a certain number of blocks before publishing again. Okay, and now let's fill that in. So what should we put in there? Well, just need to last publication block number plus minimum publication period number minus block number. That's the number of blocks we have to wait. And then, of course, at this stage, we can't publish yet. So we'll also disable the publish button. Publish button dot prop disabled true. Otherwise, we can reset the publish wait message to you can publish whenever you want. So we'll just copy that from up there. And we will re-enable the publish button. Actually, let's copy that from here and simply change that to false. And in any case, we can also hide the progress indicator. Okay, let's just add a catch right there. To handle errors, console.error error. And of course, let's not forget to hide cover spin. Okay, so first off, we show the footer with the publish and the close button, and we hide the your support div. Then we retrieve the episode counter value from the contract because we need to know whether an episode has already been published or not. If no episode has been published, we enable the publish button. We add a message to the footer to let the user know that he can publish right away. And we stop the loading. our job is done. Now, if an episode has already been published though, we need to investigate further to figure out when this episode was published. If it was more than minimum publication period blocks ago, the owner can publish a new episode again. Otherwise, he can't. So we call the last publication block getter on the contract and we save it in a local variable. Note that, again, unsigned integers are returned as a special big number type in JavaScript, and that makes calculation a little hard, so we convert it to a regular JavaScript number. We need another piece of information, the minimum publication period, which we also retrieve from the contract, convert to a number, and store in a local variable. And last element we need is the current block number, which Web3 can provide to us with eth.getBlockNumber function. Again, at this stage, Web3 functions don't use promises yet, but they will in the next major release. So we use a callback function, and in there, if the current block is before last publication block plus minimum publication period, the owner can't publish yet and has to wait a certain number of blocks, so we display that information. Otherwise, the owner can publish right away. In both cases, our job is done. So with that, we can save the file, go back to the page, and as you can see, the Your Support section does not show. Let's refresh the page to make sure that we are up to date. Yes. So here we are connected as the first account in Ganache, which is the same account as the one used to deploy the contract. And as a result, we can see the close button, we can see the publish button, and we can see the message that says you can publish whenever you want, since we have not published any episode yet. So that's correct. Now let's have a look at the refresh supporter data function. Let's implement that one. So in that case, we show the Your Support section, but we hide the owner footer. Then let's declare a local variable called per episode that will contain the pledge per episode amount. And we call series.pledge per episode. This returns a promise, so then function pledge per episode, and we set the value on our pledge per local variable, called per episode. Then we load another element from the series contract, which is the pledge amount for the current user. So that's where we use the account parameter. And then we can chain a then function that will take the pledge and then we have several cases. So if pledge.toNumber, again, it's returned as a big number, so we need to convert it, is equal to 0, then we can disable the withdraw button because it doesn't make any sense to withdraw a pledge that is 0. So prop disabled true. And also we change the text of the pledge button to be support instead of increase. Else we re-enable the withdraw button. Well, basically, let's copy that. So now the withdraw button is enabled and the text should be increase instead of support. Okay, so that's to adapt again the user interface to the state of the contract. Another thing that we can do is display a special message if the pledge is below a certain level, and especially if the pledge is below a pledge per episode. And that's why we loaded the per episode thing. So if web3.fromWay of pledge, so again, pledge is an amount in Way, so we can convert it to an amount in Ether. Web3.fromWay per episode, and again, as a second parameter of FromWay, we can always specify the unit we want to convert it to be more explicit. By default, it's Ether, I think, but it's better to make it explicit. And then in that case, pledge to low warning dot show, and we'll define this element in a minute. And otherwise we just hide that element. Now let's get pledge Ether into a local variable. And set it on the pledge Ether span. And then we can also update the text of the pledge episodes span to be math.floor of pledge divided by per episode. Okay, so we just divide the amount of the pledge by the pledge per episode to get the number of episodes that this corresponds to. And then we can use the get ether price function, again in euros, function price. And once we get the price, let pledge fiat equals plus price multiplied by web3 dot, well, let's use actually the pledge at variable that we declared before, to fixed 2 plus euros. So actually we don't need that part to convert it into a string. And once we have that, we can set it on the pledge fiat element. And that's it. The last thing to do is just to hide the progress indicator, and we don't wait for CryptoCompare to return the price for that. And last but not least, let's just handle errors with a catch block. Console.error error, and let's not forget to hide the progress indicator anyway. Okay, so again, in this case, we show the support section and we hide the owner footer. Then we retrieve the pledge per episode from the contract and the current user's pledge. If this pledge is 0, we disable the withdraw button and we change the text of the support button to be support. Otherwise, we enable the withdraw button and change the text of the support button to be increase. Then if pledge is below pledge per episode, we show a warning to let the user know that he's not participating in the funding of the next episode. And finally, we display the amount of the pledge both in Ether and in euros, and the number of episodes this corresponds to. Pretty straightforward. Now we're almost done with showing information, but there's one more thing that we need to do. Basically, when you log out from within MetaMask and reload the page, so let's go back to our interface now. And so for now the interface is consistent, but if we go to MetaMask, click the settings button in the upper right corner and click log out, this locks the MetaMask vault. So now no account is selected. If we go to the page and refresh it this time, we can see that the interface is inconsistent because it shows everything. It shows both the your support section and the owner-specific footer. So let's handle that case better by declaring a new function in the app object in app.js called refresh. Let's go back to app.js. And right after the start function, I'm going to define a function called refresh that takes an account. Again, let's not forget the comma. And in this function, we will first refresh the contract data, whatever happens. And then if account is provided, so if account is trueish, meaning it's not undefined or null, then we will hide the no account info section, and we'll define that in a second in the HTML. But we can show the your support section, and we can refresh account data for account. Otherwise, we will actually revert that. So we'll show the no account info section and we'll hide the your support section. Of course, I need to call that refresh function. So now, instead of those two lines, I will replace those two lines with app.refresh and pass the account. And now we can remove the test. Okay, we can remove this test. Actually, that displays the alert if account length is 0, because now we're handling that case. And if we go back to the interface and reload the page, we can see now that the your support section has disappeared. So that's okay. And the the owner footer still appears, but we'll fix that in a second. For now, let's add that warning message to index.html. So let's go back to index.html. And before the your support section, we'll just add a new div. With an ID of no account info and a class of alert info and card body. Okay, you can expand that message as you like to give a maximum of info to the user in case MetaMask is not unlocked. And last but not least, let's change the owner footer section in index.html to hide it by default. So the owner footer section will just add an inline style of display none, so that the owner footer does not appear until we explicitly ask it to do so. Now we save all that, we go back to the interface, and we can see that the owner footer has disappeared because we are disconnected, and we can see our warning here that invites us to install the MetaMask extension and unlock the vault. Okay, and if we unlock the vault again by entering our password and reload the page, then we can see the full interface. And actually here, what's the account that's connected? Ah, yeah, that's another account than the one that, because by default, when we unlock the vault, it connects with the first account, and this one was not the, it was another account than the one that deployed the contract. So now that we selected the first account, we can reload the page and we can see the owner bar appearing, and we can see that we don't have any support or specific information. On the other hand, if I switch to the Ganache 2 account and reload the page again, then the owner footer is gone, and actually there's an error in app.js because we have a typo per episode. So app.js, let's look for this per episode. Yeah, this is not right. Now we can refresh the page. We don't have any error anymore, and the interface is consistent. The withdraw button is disabled because the current pledge is 0. So this is exactly what we wanted. And this is how we display all the information coming from the contract, both the generic information about the contract itself and the specific information regarding the account that's currently connected using MetaMask, if any. Now, the final stage, the final step in this project is to implement the functions behind those 4 buttons for transactional functions. Now let's start with the pledge implementation. The general logic for our action will be to show a model dialog with a confirmation message, sometimes with additional information to provide in a form, and then when the user confirms the dialog, we call the appropriate function on the contract. So let's start by creating the model dialog for the support button, and we can add the following at the end of the body in index.html. So let's go back to our text editor, index.html, and just before the first script, we'll add a div. Actually, I can go back to get bootstrap.com and use some of the templates there. So I can go to components and then model. And right there we have a large model that we can use. Vertically centered, that's the one. So let's use this as a template, copy that into our page. Okay, so here, this model will be called support model. Okay. Labeled by support model label. Okay, we can close this to give it some room. And then we need to change this support model label, and the title of this model will be support, and then we can have a span with an ID of support model series title, so that we can show to the user which show he is about to support. Okay, the rest doesn't change. It is a model dialog centered. Actually, we'll just add here a model LG class to make the model dialog larger and give it some room to have our form later on. And then the buttons will be cancel instead of close, and instead of save changes we'll have confirm support. And we'll also give them some IDs. So ID equals support confirm button. And we'll add an on-click event handler. That will call the pledge function that we'll define in a second. Okay, now the only thing that's left to do is to define the content, so the body of that model. So inside the model body tag, so the most interesting part, of course, is the model body div. This dialog is probably one of the most important ones of the app, so we'd better be careful about it. We start by explaining what supporting this show means and the guarantees that the smart contract offers, and we'll even add a link to the smart contract on the block explorer so that people can check which contract we are talking to, as well as its balance, its transactions, and so on. On the mainnet, we'll even associate the source code of the contract to this so that people can check the source code from there. There are also a few values in this dialog that we need to inject, like the minimum publication period and the pledge per episode. Then there is a form where the user can define how much money he wants to pledge or how many episodes he wants to support. And both fields have onChange and onInput event handlers so that we can automatically adapt one as a function of the other using JavaScript. And in the footer, we have a cancel and a confirm button. Now let's modify the pledge button in the interface itself. So here, the pledge button. We'll just add a couple of arguments. So data toggle equals model and data target equals hash support model. Okay, so this just instructs the button to open the model when clicked. With that, we can save the file, go back to our user interface. We have no error here. We are connected as a supporter, as a potential supporter anyway. And then when we click the support button, we can see the dialog appear with all our guarantees, our text for explanation, and both our fields that allow us to set the support for, the support either in number of episodes or in Ether pledged. And obviously we need to fix the title of the dialog, the link to the smart contract, the pledge per episode, and the publication period. So to do that, we go back to app.js. And the title can be updated in refresh contract data. So in refresh contract data, as soon as we have the title, in addition to setting it to on the main interface, we can also use jQuery to set it directly on support model series title .html title. If I do that, I save, I go back, I click the support button, and now I can see support proof of cast. Let's do the same thing for the other pieces of information. So the link to the smart contract can be updated as soon as we get the instance of the contract, because then we can have its address. So right above that, in the first then block, we get the instance. And in there, what we can do is use again jQuery to put support contract address and set the href prop to be etherscan.io/address/plus instance.address. So that's the URL format for the Etherscan website. And etherscan.io, you can check it out. It's a block explorer for the Ethereum main chain. So of course, this link will only be valid once our interface, our user interface uses a contract on the main chain. There are other addresses for Etherscan on other test networks and so on, but we won't go into that. Okay. Next, we can adapt the pledge per episode, and we load it here. So right after we set it in the main interface, same thing. We can go support ETH. So we can set it, set the value of the support ETH input in the form to be by default the support for one episode, because that's the default also value in number of episodes. That's the minimum basically. So from way pledge per episode in Ether, and of course we want to convert it to a number, and we can also display it in the dialog itself with support pledge per episode .html, and that's basically the same thing as here. Okay. And again, note that the default number of episodes to support is 1, so we also initialize the pledge in Ether to the value of pledge per episode. And finally, for the publication period, so this is loaded here. And in addition to setting it on the main interface, we can go to support publication period blocks. Yes, that's the one. .html plus minimum publication period. And with that, if I go back to the user interface, reload the page just to be sure that I'm up to date, click the support button. Now there is a link, as you can see at the bottom of the window here, and it leads to etherscan.io. I can see that every time the producer of this show publishes a new episode, your pledge will decrease by 0.005 Ether. So that's okay. The value of this field is also initialized correctly. And the show producer has to wait at least 0 blocks after a publication to publish again. That's wrong. Yes, that's because I didn't use the right sign here. Quite strange. I don't know what it gives when you divide a string by something else, by a number. So let's check that out now. Yeah. So now the show producer has to wait at least 80,640 blocks after publication to publish again. So now our dialog is correctly initialized. Now let's declare the functions that will update the fields of our form based on one another's value. Again, in app.js, maybe after, just before get ether price, for example, we can go to, implement a function called support episodes changed. That will be a function. Up, and then we'll just get our support episodes field. That is just to avoid calling this selector multiple times. Support episodes, and let support confirm button. We also need a reference to that. Okay. So with that, if support episodes field.val, that's the value of this field. If it's truish, meaning it's defined and positive, let series, if the value is not undefined, that is, so series.deployed, again, we reload the deployed contract, then function instance, series equals instance, so we initialize our local variable to store the reference to the deployed contract, and then return series.pledge per episode. So we load the latest value of series.pledge per episode, then function pledge per episode, and there we can support eth.val. So again, this function is called when the number of episodes in the form changes. So here, pledge per episode. So we're converting the pledge per episode to ether, and we're multiplying that by the number of episodes that is set by the user. Okay, and of course, at this point in time, we can consider that support episodes field is not invalid, so we can remove the class is invalid in case it's there, otherwise it just does nothing. And finally, support confirm button dot prop disabled false. Okay, else, so for example, if we completely remove the value in this field, this time we will support episodes field dot add class is invalid, and support confirm button dot prop disabled true. Okay, and that's it for the implementation of that function. We can also implement the other one. So support ETH changed is also a function, and there we'll take a reference to the support ETH field, and to the support confirm button. And if support ETH field.val. So if we have a value, and this time we need also to check that it is numeric, because the input is of type text and not number. So we have no guarantee that it's numeric. And we also need to have this value be positive. Okay, we'll see what we do in the else case afterwards. So in that case, same thing as before, declare our local variable series.deployed.then function instance series equals instance, and return series dot pledge per episode. So again, you've seen that now quite a few times. Yeah, it should not be surprising to you anymore. So this time we're trying to deduce the number of episodes from this amount. So that will be math.floor of support ETH field.val divided by web3.fromWay pledge per episode in Ether. Okay, it's important to work with the right units there. Then once we have this value, we can set it on support episodes with the val function as well. So number of episodes, okay. And then support ETH field, we can remove the class is invalid if we ever added it before. And we can enable the support confirm button by calling the prop disabled false function. Okay, and otherwise, of course, support ETH field, we add the class is invalid and we disable the support confirm button. Okay, so note that with this logic, if you manually enter 0 as a number of episodes, it's considered as invalid. But if you type an amount in Ether that's less than pledge per episode, you will support 0 episodes with that pledge, but it's possible that the sum of this amount and what's already in your pledge in the contract represents more than pledge per episode, in which case your pledge will be allowed. Now, the last piece of the puzzle is to implement the pledge function called when the user hits the confirm button in that model. Before we do that, let's just check that the implementation works and that we don't have any error for those two functions. We save the app.js, we go back to the interface, we reload the page. Let's hit the support button and change the number of episodes, and we can see that the amount of Ether is adapted accordingly. And if we change, for example, to 1 Ether, we see that isNumber is not a function. Yeah, because that's not isNumber, it's isNumeric. So here it's isNumeric. That's the correct function that we need to call on jQuery. Save again, go back. Support. Now let's set, for example, to 0.5, and you see that every time we type something, we change the number of episodes that are supported behind the scenes. So both fields change based on one another. And if I completely remove the value in support the show for, then it's marked as invalid. I cannot type any kind of text in there. And of course, if I remove completely the value here, you see that the confirm support button is disabled, and the ether field is marked as invalid. So the logic for our function is correct. Now let's go back here. And as I said, the next step is to implement the pledge function called when the user hits the confirm button in that model. So let's do that now. Pledge will be a function, and we'll first retrieve the pledge value from the form. So that will be support eth.val. So if is numeric pledge value and pledge value is positive, otherwise it doesn't make any sense to do anything, then we start our asynchronous activity. And so for that, we'll just display our progress indicator. Then I'm going to use the Web3 library again to load the latest list of accounts, just to be sure that I have the latest ones. Error accounts. Okay, and in that callback, if accounts and accounts.length is greater than 0. In other words, if MetaMask is correctly unlocked and we have selected an account, then I need to load the deployed instance of the contract. Then I need to convert the pledge value into Way. So we have it in Ether and we want it into Way so that we can call instance.pledge. And when we call a transactional function like that, remember that pledge doesn't take any argument in the contract. Truffle contract abstraction adds a special argument for us that allows us to specify the characteristics of the transaction itself. So here we want to call that function from accounts 0. Of course, the name of the keys is very important. Value, that will be the value that we just converted. And then we also need to specify the gas, and that is the gas limit. So that's the maximum number of gas units that we are willing to pay for. And in that case, we'll just set that to 500,000. That's an arbitrary number, and that should be enough for any case. And of course, then we can adapt that. And I explain that later. So once this is done, we will have another then block, and this time we will receive as a result the transaction receipt for that transaction. Let's log it, by the way, so that you can see what's in there in the console later on. And there I'm going to parse as an integer a field of this result called result.receipt.status. And that gives me an idea about whether the transaction was successful or not. I'll explain that in a moment. If the transaction was successful, we can hide the support model. And that's the way you do it with Bootstrap. Then we can reset the support episodes. field to be 1. And then just to be sure, we can recall support episodes changed, so that the value in Ether is also adapted. And if the transaction was not successful, then console.error, transaction didn't succeed. And after all these thens, I can just add a catch block and make sure that cover spin is hidden, and that I console log this error as well. And the last thing is, if the value is not numeric or is not, sorry, that's not what I wanted to do. If accounts, that's the if I want. Yeah, so if no account is selected, then we can hide the progress indicator as well. Okay, so first we get the pledge value in Ether from the pledge ETH field. If it's numeric and positive, we show the progress indicator and we reload the connected account, just to make sure that we have the right one. Then we recover the instance of the contract, convert the pledge value to way, and call the pledge function on our contract. Again, in our Truffle contract abstraction, in addition to their arguments as declared in the contract function, transactional functions take an additional JavaScript object to define the parameters of the transaction, like the value, which is the amount of money we are sending to the contract as part of the transaction. That only works for payable function and can be retrieved from msg.value inside the contract. Then we have the from field, which corresponds to the address we want to send the call to that function from. And finally, we have gas, which corresponds to the maximum gas we expect this function to require, knowing that if it consumes more than that, we will pay this gas, but the function will throw an exception. Now for the gas value here, we specify an arbitrary value of 500,000 units, which should be more than enough. Then we can have a look at how much the transaction really consumes in Ganache and adjust that amount accordingly. Note that if there is a bug in the contract function that throws a runtime exception, all that gas will be consumed. So that number should be big enough to cover for the real complexity of the function, but not too big either. Otherwise, the user will lose all of its gas if there's a bug. This number only depends on the complexity of the code in the function, so it's the developer's job to determine the right value for it. Then, to know the real cost of the function call in Ether, we have to multiply that value by the gas price, which is the price of 1 unit of gas. And this gas price is defined by default by MetaMask, but the user can customize it when he confirms the transaction later in MetaMask, and we'll show you how it looks like. What it looks like. The higher the gas price, the faster the transaction will be processed. That's the only thing that you need to remember. Then the then block here is only triggered when the transaction has been mined, and what we get as a result parameter is the transaction receipt. Now, certain Ethereum node implementations don't throw an exception when the transaction fails. So we check the value of result.receipt.status to be sure it was successful. And if so, we hide the model and we reset the fields of the dialog's form. Now let's test that function. So again, we save our app.js. We go back to the interface. We are connected to the contract as the Ganache 2 account, I guess, yeah. And the balance for now is 100 Ether. Okay, so everything's correct. Now I can click the support button. Let's say that I want to pledge 0.5 Ether, which corresponds to 100 episodes. When I click confirm support, MetaMask intercepts the transaction and shows us this dialog. In this dialog, we can see the gas limit as we define the default value for it in the JavaScript in app.js. So that's 500,000 units. The default gas price is 1 gigaway. So 1 gigaway is 1 billion way. So that's 10 to the minus 9 ether. We can see that the max transaction fee, that is, if I consume all those 500,000 units, it will cost me this transaction fee. So 500,000 units times 1 gigaway is this amount in ether. Okay, and that corresponds to about 25 cents of a dollar. I can also see the amount that I'm sending, so that's 0.5 ether. And I'm sending them from this account right there that has this balance right now, and to this address, which corresponds to the address of the contract. And I'm connected to the private network. So all the information, all the relevant information is visible in that box, and I need to check it before I either reject or submit the transaction. So if you reject the transaction, we'll see the error because we are logging all the errors. Okay, so that's normal. And the progress indicator disappears and nothing has changed in the interface. We can still modify something. And if we go back to MetaMask, by the way, we can see this transaction here and we can see that it was rejected. Okay, now let's confirm support again. But this time we'll submit the transaction. We can see the transaction receipt in the console log, and the progress indicator keeps spinning. And that's normal because we didn't do anything to hide it in case the transaction is successful. Now, what we can do though is have a look at the interface in Ganache. In the transaction screen, sometimes there's a problem with the user interface in Ganache. Here, the transactions all disappeared, even though they are there. Can I still see them in the blocks? Not really, because I can only see a few blocks back. Anyway, so now if I go to the MetaMask extension, I can see that my account doesn't have 100 ether anymore, but it has almost 99.5, because in addition to the 0.5 ether that I paid to the function, I also paid a small amount of transaction fees. So that's why it's a little less than 99.5 ether. That's the balance. And you can see that the transaction is confirmed here. So now if I reload the page, I can see that my pledge is 0.5 ether, which corresponds to 214 euros and stands for 100 episodes. And by the way, you can see now that in the supporters section, I can see that there's one active supporter, one follower, and the next episode will be paid 0.05 ether. So everything is consistent except for the progress indicator that remains on screen. So basically the issue is that we don't hide the progress indicator when the transaction was successful, and that's on purpose. Because the surest way to know that a transaction was processed and the contract state was updated is to watch for events. In this case, we should refresh the whole interface when a new pledge event is triggered. So let's start by adding a watch events function. Let's go back to app.js. And here, maybe before the refresh function, let's declare a new watch events function. And this function will load the deployed instance of the contract. And once it's got this instance, we can use it to watch the event. And to do that, we call the new pledge function. Well, it maps to the event. I'm going to pass two empty JSON objects, and I'll explain that in a moment. And then I call the watch function on it. And this one just takes a callback function. in there app dot refresh account. So that means that the watch events function also needs to get the account. So this function is pretty straightforward. It retrieves the instance of the contract and then watches all events of type new pledge on that instance. The two empty object parameters that are passed to the event correspond to the scope and the filter of the watcher. Scope is the range of blocks on which you want to listen to events, and filter allows you to get events only when certain indexed fields have a certain value. Since for both of these we set an empty object, we are watching for all events on the whole chain. And when such an event occurs, we just refresh the whole interface. Now, let's call this watch events function right after refresh in the start function. Watch events account. And we can go back to the browser, refresh the page. And now let's try to increase our support, for example. Add support for 10 more episodes, for example. Confirm. Submit. And after a few seconds, the model disappears. And the progress indicator disappears as well. And now we can see that the interface has been updated and we are now supporting for 110 episodes for 0.55 Ether. And if I look at the balance for that account, yeah, we can see it has decreased a little more. Not too bad, huh? And now everything is in place. We just need to repeat the same process basically for the other functions, starting with withdraw. Now the basic principle for withdraw will be the same, except the dialog will only be a confirmation dialog without any fields to provide any value, since the withdraw function in our contract is not payable and doesn't take any parameter. So let's start by adding the model dialog to the index.html file. And for that, we'll simply take the dialog that we had for the support model and we'll copy paste it below. We can remove the body, so the content of the body div can go, and then we'll just here have the withdraw model as an ID labeled by withdraw model label, which we need to set here. The title of this will just be withdraw, for example, with a question mark, and that's pretty much it for here. Then the first button will be cancel, and the other one will be yes, please give me my money back. Okay, and here we'll call the withdraw function on the app object. No need to pass the event. Okay, then in the model body, we can simply add a small paragraph for explanation. It says, if you withdraw your pledge for and that will be withdraw pledge ETH, you will get all of it back minus the fees for this transaction, of course. but you will no longer support new episodes of this show. And then we ask the question, are you sure you want to withdraw? And that's it. That's all this dialog does. By the way, for this one, we can remove the model LG class on the model dialog because we don't need that much space. What we do need though is to update the withdraw button right here. So we need to add data toggle equals model, data dash target equals hash withdraw model. Now let's go back to app.js and update withdraw pledge ETH as soon as we retrieve the current pledge of the user in refresh supporter data. Refresh supporter data is right here. We retrieve the pledge for the current user in here, pledges account, and we set it on pledge ETH, pledge episode, so we can add just a small line here to say withdraw pledge ETH dot HTML pledge ETH. And again, you can do the same in fiat currency also if you want to display that amount as well. Okay, then let's implement the withdraw function as well. So after the pledge function, withdraw will be a function that doesn't take anything, but does the same as before. So we can just okay. So here I'm loading the accounts again to make sure I have the last one. I'm checking that we have at least one account selected. And if that's the case, we can actually hide the withdraw model right away. No need to keep it on screen, even if there is an error. It's easy to display it again. There's no value to keep track of. So we can hide it right away. We can also display the progress indicator. So cover spin.show. Then we load the deployed instance of the contract, and we can call instance.withdraw on that. Again, the withdraw function doesn't take any parameter in the contract, but we have to specify some transaction parameters. So we want to call that function from account 0 and with a gas again of an arbitrary amount of 500,000 units. And with that, we get a function that receives a result. And if parse int of result.receipt.value is 1, then that means the transaction was successful. Actually, we only want to display a message if it's not 1. Console log error. Actually, transaction didn't succeed. And in any case, we need to handle errors. So catch function error console.log error. And finally, we need to hide the progress indicator. So that's our implementation of the withdraw function. Now, of course, we also need to watch the withdrawal event in watch events in order to refresh the interface when our withdrawal has been processed. So we can go back up to the watch events function, and we just copy that element, and instead of watching the new pledge, we'll watch the withdraw event. Same parameter, same thing, and we refresh the whole interface when it happens. Now let's go back to the interface, reload. Everything is as before. Now we have some support, so the withdraw button is active, is enabled. We can just click it. We can see our confirmation dialog. If we withdraw your pledge for 0.55, okay, we missed the unit here. You will get all of it back. Are you sure you want to withdraw? Yes, please give me my money back. We are sending a transaction to our Ethereum node. So MetaMask intercepts it. Again, if we reject, nothing happens. And if we submit the transaction, after a couple of seconds, we get transaction didn't succeed. Why is that? That's because we're checking the wrong value. We're checking result.receipt.value, and this is undefined. So indeed, transaction was not successful, even though we can see that the user interface was correctly refreshed, and now we're supporting 0 episodes for 0 ether. So it was actually done correctly. It's just that it's an inconsistency, a typo in our code. So we are going to check that. First of all, let's go back to index.html and fix our model to add the ETH unit. If you withdraw for ETH, and then in app.js, instead of checking receipt.value, we check receipt.status. By the way, here you can see now the transaction appeared. So this is the contract call that we just did to withdraw. And you can see the gas that was effectively used. So if you go here, we can see that the gas limit was 500,000, but the gas really used was 22,321. So we could adapt the gas limit to be closer to that number. Not exactly that number, because we need to leave some margin for error, but still we can get closer to that if we want. Okay, now let's go back to the interface and try again to support, let's say for 100 episodes, we confirm support, submit, we wait a couple of seconds, and the interface is updated, and now we can withdraw 0.5 ether. Yes, please give me my money back. Again, we submit the transaction, and this time everything is okay. And just like that, our community members can now support several episodes of our show in advance and withdraw their support too. So we handled both actions that are available to supporters. Now let's tackle the actions for the owner itself. Now for publication, we have one parameter to provide to the publish function, that is the link to the episode. Transactionally, this might not have a lot of interest, but it might help to reassure supporters if we record and display links to the episodes in this interface. We won't actually do it in this tutorial, I'll leave it as an exercise at the end. So let's start by creating the publish model in index.html. So again, we go back to our text editor, index.html. Let's copy this model, paste it. We'll call it publish model, labeled by publish model label. Publish will be the title of So publish a new episode, for example. Okay. And that's pretty much it. Yeah, let's add a model-lg class to make it large. Now let's define the body. Well, first, let's clean up the body. Change the title, the text of the button. So the confirm button will be publish confirm button. And it will call the function app.publish. And the text of the button will be publish episode. And that's it. Now we can define the body. So first of all, let's add a new paragraph. It says, please specify the link of your episode down here and make sure it's valid. If supporters can't find your episode there, they will probably withdraw all their pledge. Again, that's to inform the user what he's doing and make sure he understands the consequence. So then we create a form, a very simple form with only one field. So div class equals form group. And this form group will only have an input, type is URL, name is episode link, ID is episode link as well, and class is form control. And the placeholder is episode link. And that's it. Div, form, and we're good. So again, the most interesting part is the model body div. They're just a simple form with a text input with a URL input for the episode link. And the publish confirm button calls the publish method on the app object, which we will declare in a minute. For now, we can add the attributes to the publish button to open the model. So we can go back to the bottom of the card with the owner footer. And in the publish button, we can add data toggle equals model, data target equals publish model. Now let's declare the publish function in app.js. So again, we go after the withdraw function, and publish will be a function that takes nothing. So let's get a reference to the episode link field. Let's get the episode link value itself. And so if episode link is provided and episode link length is greater than 0, let's define episode link field dot add class is invalid. In other words, if we don't provide any link, this episode link field is considered as invalid. And we can also get a reference to the publish confirm button. And say that publish confirm button dot prop disabled true. So we can disable the publish confirm button if the field is invalid. If it is valid, well then, first of all, episode, let's just copy those 2 lines, paste them here. Can remove that class and disabled false. Then we load the accounts. And if accounts and accounts dot length is greater than 0, can do something, and that is first show the progress indicator, cover spin dot show. Then we load the deployed contract. You know the drill by now. Not instance, but instance. And then we can return instance.publish. This time we need to pass the episode link as a first parameter. And then the second parameter is just the JSON object, JavaScript object to specify the parameters of our transaction. From, and the gas will be 500,000. Again, no value since the function is not payable. Then function result. Again, we get the transaction receipt. And we need to check its status. Result.receipt.status. If it's 1, it means the transaction was successful. So we can hide the model. Otherwise, console.error transaction didn't succeed. Okay. Then let's just add a catch block. And as always, we log the error and we hide the progress indicator. And that's it. So we start by keeping references to the episode link field and its value. And if the value is not provided, we mark the field as invalid. We disable the support button, the support confirmation button, and we stop right there. If it's valid, then again, we refresh the current account, we show a progress indicator, we retrieve the instance of the contract, and we call the publish function on our contract, passing episode link as a first parameter. As before, the last parameter specifies the characteristics of the transaction in which this call will be made. So no value since the function is not payable, but a from address corresponding to the account currently selected in MetaMask, and a gas amount corresponding to an arbitrarily large number to be fine-tuned later. And once the transaction has been mined, we receive a transaction receipt on which we check the status and hide the model if it was successful. And at this stage, we don't hide the progress indicator yet, because this function is supposed to emit a new publication event that we need to watch to refresh the interface. And for that, we need to modify the watch events function. to add another block like this to watch the new publication event. Now we can test this feature. Let's go back to the page. Let's add some support. So we're still connected as a potential supporter. Let's add some support for 10 episodes, for example. Confirm. And now I pledge 0.05 Ether for 10 episodes. Now in MetaMask, we can switch to the account Ganache 1, which is the account corresponding to the owner of the contract. We reload. Okay, so we can see that there's one active supporter and that on the next episode I should be paid 0.005 Ether. Okay, and I can publish whenever I want. So I hit the publish button. Here I can specify a link. Let's say this is the link of the first episode of the Proof of Cast podcast. Okay, I publish the episode. As always, I can reject the transaction at this stage, or I can just submit it. Transaction gets mined, and the interface is updated. And as I can see now, the publish button is disabled, which is wanted. And then I can see the message that says you have to wait for 80,639 blocks before publishing again. And of course, every time I refresh the page, this number decreases. And I know how long I'll have to wait before I publish the next episode. Now, if I switch MetaMask to the other account, the supporter account, Ganache 2, and I refresh the page, I can see that my remaining pledge is for 9 episodes left, because one was already paid to the show creator. So everything is consistent. On to the last feature of this application, the ability to close a show. Now, of course, the close operation will be a pretty drastic one, so we want to confirm it with a dialog. So let's just go to index.html again. We'll copy the withdraw dialog, the withdraw model. That's the closest one we have. We'll add that at the end of the body. That will be the close model with a close model label. Okay, change the title, and now we have a message. So if you close this show, all the pledges will be sent back to your supporters, and this contract will be disabled, making it impossible for people to contribute to it again, at least not at this address. Okay, so again, we explain that. Are you sure you want to close this show? And first button is cancel. The second one we call the close function in the app object. And yes, close this show. Okay, this is just a confirmation model. As always, let's not forget to add data attributes to the close button in the owner footer. Close button data toggle equals model, data target equals hash close model. And now let's add the close function to app.js. So web3.eth.get accounts function error accounts. So same logic as before. If accounts and accounts.length is greater than 0, then we show the progress indicator. We load the contract instance again. And with that instance, we return instance.close, and we simply pass one JavaScript object with the characteristics of the transaction. From that, we get, in the next then block, we get a function that takes a result. And as always, we need to parse int the result.receipt.status. And if it's 1, it means the transaction was successful, so we can hide the close model. Otherwise, console.error transaction didn't succeed. And in any case, we need to catch our error function error. And that's it. So we reload the accounts from MetaMask, show the progress indicator, and call the close method on the instance of the contract that we recovered. And there is no parameter to pass except for the transaction details. And when the transaction has been mined, we check the receipt status. Of course, we also need to watch for the series closed event. So we go back to watch events again. And we add a new block like this. Series closed. And now, of course, the question is, what should happen to our user interface once the contract is disabled? Well, quite simply, every call to one of its functions, including getters, will fail and throw an exception. And in that case, it makes no sense to display the information about the contract. Instead, we'll replace the title of the show with a message that explains that the contract is not available anymore. To do that, let's declare a new function. So after refresh, for example, let's create a function called display show cancelled message. There's a function. And we'll hide a certain number of segments. Let's copy that a couple of times. So the segments that we want to hide are show info. Doesn't make any sense to show it then. Supporters, same thing. No account info should be hidden as well. Your support and owner footer. We don't need those, but we'll need to set title to some HTML, and that will be this show was cancelled. you cannot support it anymore. And then the whole interface will be hidden basically. And of course, we don't forget to clean the progress indicator as well. And then in refresh contract data, again, if the contract is disabled, the first call to one of its functions, so here, for example, the series.title, will crash and will throw an exception, basically. So we just need to make sure that this series of then blocks has a catch in the end. And it does. So here, instead of this coverspin.hide, we'll replace that with app.display show cancelled message. And again, this catch block is valid for all the chain of promises, and so as soon as it happens, we get into that block. Now let's go back to there. We can switch back to the account that corresponds to the owner of the contract. And we can see that the close function is still available. We just click that button. Let yes close this show. A new transaction. We submit the transaction. And after a few seconds, the event is emitted. We get this exception that's logged, and that's normal. But now the whole interface is replaced with this show is cancelled and cannot support it anymore. And even if you reload the page, you'll always get the same result. So now our contract is not usable anymore. And the only way that we can reopen the show basically is to redeploy the contract and to give that address to our users again. By the way, when we closed this, it's kind of hard to show. But when we closed this contract, of course, every supporter was paid back and recovered their funds. If we go back to here, we can see the last contract call is here, and we can go to the accounts and see that the one that had supported is now almost whole because his balance is 99.99 Ether. And of course, the difference corresponds to all the transaction fees that he paid each time he supported and withdrew, and supported again. And that concludes our implementation of the Crypto Series application. Just like that, we implemented a decentralized version of Patreon with Ether payments. We saw a lot of Ethereum and blockchain concepts, including the architecture of a decentralized application, the main development tools that you can use to develop one, how to create a project in Truffle, how to write a simple smart contract in Solidity, state variables, access control, view transactional and payable functions, events, Web3.js and MetaMask, SafeMath, and other OpenZeppelin tools, the whole shebang. We sure covered a lot, but this was just an introduction to the topic again, and there are a lot more topics to talk about, like how to test your contracts before deploying them, which, as I'm sure you understand, now is very important. How to deploy your contracts to test networks and to the main production network, and in general, how the blockchain works under the hood. And we didn't even talk about cryptographic primitives, which are also important to understand. So again, if you want to learn more about all that, feel free to join more than 11,000 students from more than 140 countries on our Udemy course called Become a Blockchain Developer with Solidity and Ethereum. And you can use the discounted link in the description down below. You can also ask all your questions there, and we'll be happy to answer them. And of course, again, if you have some ideas for the next videos or some feedback about this one, please comment below. And finally, if you want to keep track of our future videos on this channel, hit that subscribe button. Thanks a lot for watching that far, and see you in the next videos. Bye-bye.